Hi students, good morning. This is Sekhar from Msigma Gokulam. Let me introduce first of all myself. Let me introduce to all of you. I am Sekhar, one of the senior most teachers in mechanical engineering with the specialization in thermal and fluid sciences. I have taught for GATE, IES for several years across many corporate institutions across India. Now I am going to teach you in these video sessions how to face the university examination, particularly KTU university examination, how you can face the examination without any much preparation. The main objective of these video sessions is to enable the student to face the examination, to write the examination, at least to score a minimum to 50 to 60 marks without any kind of preparation. Suppose most of the students generally nowadays, they just open the books majority, because I know the student psychology, because I've got more than 30 years of experience in teaching. Many students will open the books just once the timetable schedule is come for the examinations. So even for those students also, we have not who have not opened the books of we don't know much about the thermodynamics, they would be able to face the examination once they see these video lectures. The main objective of these video sessions is that keeping in mind those students who have not at all opened the books, or don't know anything about the thermodynamics in their preparation. Those who have already know the student thermodynamics also, those students, they could definitely score 15 to 20 or 25 marks extra once they go through these videos. Okay, let me start this one of the most important subject of mechanical engineering called thermodynamics. A very important subject, because this subject lays the foundation. Thermodynamics lays the foundation for understanding many other subjects of mechanical engineering, like thermal engineering 1, thermal engineering 2, refrigeration, air conditioning, etc., etc. So even the thermal turbo machines, steam turbines, gas turbines, IC engines, refrigeration, air conditioning, to understand all these concepts, thermodynamics is the foundation. So the concepts what you learn in thermodynamics is very much essential to prepare for the other subjects in future, like maybe in 3.1, 3.2 of mechanical engineering. So let me start with the thermodynamics now. The very name thermodynamics tells about this two forms of energies. Thermo is connected with heat energy, generally denoted with Q. Dynamics is the word pertaining to the work, generally denoted with the W. Thermodynamics is the subject that deals with two basic forms of energies, that is heat energy and work energy, which are mutually convertible into each other. Heat and work, these are the two major forms of energies which we talk about throughout the subject. Heat energy can be converted into the work energy, and work energy also can be converted into the heat energy. So thermodynamics deals with two basic forms of energies, that is heat and work, which are mutually convertible into each other. Which are mutually convertible into each other. In fact, I will give the best example for this statement in the form of the internal combustion engine, which is the heart of any automobile, any car or a bike or a bus or even the aircraft or anything that moves, what you see on the road or in fact in the air. We see they are all the prime movers. They are being driven with a prime mover with the help of the heat energy derived from the combustion of a fuel. For example, you have got a bike, so maybe a 4-stroke bike or a 2-stroke bike, where you are burning the petrol inside the engine. The heat liberated due to the combustion of the petrol is the main source of energy, heat input to the engine, which is being converted into the work. Using that work, you are able to drive the bike. So how a bike or the car is being driven Because of the heat generated inside the combustion chamber of the engine, that due to the burning of the petrol, or if it is a big truck or a bus, the fuel will be diesel. But whether a petrol or a diesel, once you burn that fuel, it liberates a lot of heat, which you call it as the calorific value. So that heat is being converted into the mechanical work. With that mechanical work, the engine is being driven, which is able to drive the car. So, so the conversion of the heat to the work is the best thing what you can observe in the inside any automobile. Example, an automobile engine. It is like this. For example, in an automobile engine, so it is a piston cylinder arrangement. You will be just spraying the petrol or the diesel, whatever it is, diesel or air fuel mixture in case of the petrol engine. That will undergo the combustion. The diesel or air fuel mixture will undergo the combustion. Undergo the combustion. After the combustion of the diesel or the petrol, there is a lot of heat being generated. Heat generated due to combustion of fuel. Due to combustion of fuel, that heat generated will increase the pressure and temperature of the gases, which is able to push the piston forward and is able to do the work. So, we are getting the work here. So, that work is converted via crankshaft into the rotation of the axle, and that power, mechanical power, will go to the wheels, with the help of which the car is being driven. So, very simple, best example is that in any automobile engine, the conversion of the heat energy, that heat energy liberated because of the combustion of the fuel being converted into the work, and that work is able to drive the vehicle. A simplest example of the conversion of the heat into the work. In fact, I will give another example. In any steam power plant, which generates around 70% of electric power what we are using in India, electric power, our life totally depends upon the electric power. 70% of the electric power what we are generating in India and you are consuming is generated from the steam power plants. How the steam power plant electric power is generated? We will have a coal. We will have a coal as the fuel. The coal is fed into the boiler furnace. We will burn the coal. That coal will undergo the combustion and liberates a lot of heat. That heat will be supplied to the water. That water gets converted into the steam, generating a high pressure, high temperature steam. That steam goes to the steam turbine, rotates the steam turbine, because there the steam expands doing work. The coal undergoes combustion inside the boiler furnace. That heat generated is transferred to the water in the boiler, generating a very high pressure, high temperature steam. That steam is supplied to the turbine, where it expands adiabatically. And you will see later in due course of time what is adiabatic means. And because of that expansion of the steam, lot of mechanical work is generated by the steam turbine. That mechanical rotational work is supplied to the electric generator. There the electric power is generated and then supplied to the grid. So that is how the electric power is generated. So there also it is a conversion of the in any steam power plant. That there is it is like this. In the boiler, simple example I am giving, in the boiler we feed the coal, and of course that coal needs air for its combustion. The coal and air undergoes, with the help of the air, it undergoes combustion, and that heat will be supplied to the water. There is a high pressure, high temperature steam. There is a high pressure, high temperature steam is generated, and that steam will be supplied to the steam turbine, where the steam expands doing work, and that will drive the electric generator and producing the mechanical work. After expansion, of course, that steam, low pressure steam, will exit from the turbine and goes to the condenser. That is a different cycle. There is a different subject that is called as the steam power plant. So I'll just give you two simple examples. One is the internal combustion engine driving the car. Another thing is the steam power plant producing electric power. Okay. And there is a third best example is a gas turbine. So gas turbine power plant which is driving the aircraft. Any aircraft, for example, any aircraft, example, this is example 2, I had given the steam power plant. Example 3, I am giving the gas turbine power plant which is driving the aircraft. All the modern day aircrafts are being driven with the gas turbines, right? So what does it contain in the gas turbine power plant? So there will be a compressor. There will be a compressor where and the air will go into the compressor, will get compressed and it will go to the combustion chamber. Here we will supply the aviation fuel. Okay, there is an aviation fuel. Their fuel is added into the air. Fuel is burned into the air, generating a lot of heat, and that heat generated will increase the pressure and temperature of the gases. Those gases expand in the gas turbine, producing mechanical work. And that mechanical work is able to drive the propeller. So this mechanical work is a gas turbine that is driving the propeller shaft or the high speed rotational propeller shaft which is able to drive the aircraft. So I had given the three best examples: IC engine, steam power plant and the gas turbine power plant. In all these things what you are observing is there is a mechanical work is being produced. How that mechanical work is being produced? At the expense of the at the cost of the heat generated due to the combustion of the fuel. That fuel sometimes in a steam power plant the fuel is coal. In your car or a bike the fuel may be petrol or the diesel. In case of the gas turbine power plant the fuel is the aviation fuel. So, but what in principle in all these examples I had given, there is a conversion of the heat energy into the mechanical work. So, thermodynamics plays such a huge role in understanding so many important devices connected to the mechanical engineering, right. So, this is the scope of the thermodynamics. Not only that, if you in your house there is a refrigerator where you are able to maintain a low temperature inside the refrigerator box, where you are freezing the water, keeping the things and making the things very cool. In your house there is an air conditioner. So AC is supplying the cold air into the room, you are feeling comfortable, you are able to sleep well. So how these devices function? Again based on the principles of thermodynamics. Any refrigeration cycle, any air conditioning cycle, they operate based on the thermodynamic rules, thermodynamic principles. So even the rocket engine, even how a rocket engine is able to be thrown into the is propelling into the space because of the high pressure, high temperature gases which are expanding in the nozzle. Again a rocket engine works on the principles of the thermodynamics. So there the scope of thermodynamics is very vast. Fine. So having understood the scope of thermodynamics, now I would like to give you the clues how to attack a thermodynamic problem. Generally, whenever you are doing a thermodynamic problem or a thermodynamic analysis of a system, you have to make three inquiries. Supposing you are reading one thermodynamic problem, how to do that problem? Generally, most of the students how to analyze that problem. To analyze that problem, we have to make three inquiries. Three inquiries yourselves. Number one, what is the nature of the working fluid inside that thermodynamic system? What is the nature of the working fluid? Is it air? Is it nitrogen? Is it oxygen? Is it steam? Is it a refrigerant? So we have to make. Number two, what is the nature of this system that is? Now I am going to define what a system, what are the classification of the systems. What is the type of system, whether it is a closed system or a open system or isolated system. Number three, what is the type of thermodynamic process? What is the thermodynamic process the system is undergoing? Whether it is a constant volume or a constant temperature or a constant pressure or adiabatic or isoentropic or isothermal, what is that process? What is a polytropic? What process? Is it a reversible or is it irreversible? All these things we have to make an inquiry. Sometimes for the inquiries what we are doing, sometimes most of the times answers will be given. The question itself, the problem itself, they will be given the data. In the data itself, we can understand whether the system is closed or open or isolated, whether the process is isothermal or adiabatic, polytropic. In the question itself, they mention, and what is the working fluid, whether it is an ideal gas or a steam or what is that. You have to make an inquiry. So once you get the answers for these three inquiries, what is the nature of the working fluid, what is the nature of the system, what is the nature of the process, immediately the problem can be very easily attempted. So first let me begin with the concept of the ideal gas, because most of the thermodynamic problems, particularly at the BTech level also, most of the thermodynamic problems what is being given in the question papers, mostly they will be asking, majority of the problems will be carrying an ideal gas. First let me introduce the concept of ideal gas. So another examples also I am writing here, the scope of thermodynamics, if you just see refrigeration systems, example 5 is the air conditioning system. So these are all the even the rocket engines, rocket propulsion, rocket. These are all the various examples, so we can understand the scope. Actually, these are all the scope of thermodynamics. I can say scope of thermodynamics in mechanical engineering. If the question is given, you can give all these examples. Now first let me introduce the concept of ideal gas, which is also known as perfect gas. Concept of ideal gas, which is also termed as perfect gas. First let me give the definition of the ideal gas. Ideal gas is the gas which obeys all the gas laws at all pressures and temperatures. At all pressures and temperatures. Ideal gas is the gas which obeys all the gas laws. In the classical thermodynamics, actually thermodynamics underwent so many changes for the last 3 centuries. In fact, thermodynamics is a recent science. If you see the development of thermodynamics, in the 18th, 19th, 20th centuries only it has been developed. All these laws were formulated, zeroth law, first law of thermodynamics, second law of thermodynamics, third law of thermodynamics. All these were formulated only 2 centuries ago only, roughly 2.5 years, 200 years back approximately. All these laws were formulated 200 to 300 years back. So they are called as a classical thermodynamics. What are the classical thermodynamics says means there are certain gas laws. That is Boyle's law, Charles law 1, Charles law 2, Avogadro's law, Joule's law, Dalton's law, Avogadro's law. There are so many gas laws are there. If any gas obeys all these gas laws at all pressures and temperatures, such a gas is called as an ideal gas, also known as the perfect gas. I will list out all the gas laws and I will state one after another. First and foremost law which was stated earliest in the history was the Boyle's law of ideal gas. The law states that for a fixed given mass of gas, its temperature remaining constant pressure is inversely proportional to the volume of gas. Pressure is inversely proportional to volume of gas. Temperature remaining constant, pressure varies inversely proportional. If the volume gets doubled, pressure becomes half. Or how do you define it? First of all, we should know how do you define the pressure. It is a normal force exerted per unit area. Pressure word is usually, pressure is the word which you talk about only in case of the fluids, maybe water or air or a gas or a vapor. All these are fluids. Pressure is talked in terms of the normal force exerted by the fluid on any solid boundary per unit area is called as the pressure. Units are Newton per meter square. If the volume gets doubled, this pressure becomes half. If the volume becomes half, pressure becomes doubled, provided the temperature of the gas remaining constant, which can also be stated as PV is equal to constant or P1 V1 is equal to P2 V2 if temperature is maintained constant. So this is called as the one of the first laws stated in the classical thermodynamics. In fact, thermodynamics later it underwent into many changes, and by the time the Einstein and Planck came, it went into the statistical thermodynamics, which goes into the microscopic details of the molecules. Okay. So initially, actually in the thermodynamic analysis also there are two kinds of analysis, microscopic and macroscopic. If you study the behavior of any system, gaseous system, in terms of the pressure, volume, temperature, which are measurable. Suppose you have a pressure gauge, you have a pressure gauge in the, when you go to the any petrol pump to measure the tire pressure, you will keep on a gauge, right? So that is a pressure gauge. So you can measure the pressure, volume, temperature, all these macroscopic properties with some instruments, like temperature is measured with thermometer. So if you analyze the system in terms of these average properties of the system, which are measurable physically, they are called, it is analysis is called as a macroscopic. Macroscopic means on the whole system is analyzed on the average basis. But what is the microscopic analysis? Microscopic thermodynamics means you go into the details of the, what is the velocity, what is the momentum of the individual molecules. Individual molecules you want to analyze, what is the individual velocities of the individual molecules changing. That is called as a microscopic. Because what do you mean by microscopic? You want to get into the details of the individual molecules and make a statistical analysis. So that is called as a microscopic thermodynamics, which is very complex. That is done with the help of the statistical thermodynamics. That is also called as the, that needs the help of the statistical analysis or average, etc. So we don't do that. All our classical thermodynamics, in what you do in our subject, in our engineering analysis also, what we do it as a macroscopic analysis of the thermodynamics. What do you mean by macroscopic? We are measuring the properties, pressure, volume, temperature, enthalpy, etc. And we are making the relations among themselves. And we want to analyze the system, we want to analyze the problem in terms of these parameters or average properties of the system, which are measurable by the instruments. But when you go to the details of the individual molecules of the system, that is called as the microscopic analysis. Okay. Right. Now this is Boyle's law stated, that is PV is equal to constant, P1 V1 is equal to P2 V2. Now the second law which I am stating is the Charles law 1. For a given mass of gas, please note that in all these statements the mass of the gas is kept constant. For a given mass of the gas, pressure remaining constant, the volume of the gas is directly proportional to the absolute temperature, T in Kelvin. T is in absolute temperature. See, what is this absolute temperature? because the temperature is one important thermodynamic property. Temperature is another important thermodynamic property, which has we have a different scales for measuring the temperature, like a Celsius scale, Fahrenheit, Ramer, etc. And apart from these three, there is a main scale what we use in thermodynamics is the absolute temperature scale or Kelvin temperature scale, which is also called as the thermodynamic scale of temperature, absolute temperature in Kelvin. That means how do you get the Kelvin? We have to add the 273.15 to the Celsius scale. What we get is the absolute. Supposing anything 0 degrees Celsius plus 273, that will obviously give the answer in Kelvin. Okay. We have different kinds of the temperature measuring scales. I will discuss it later. Celsius, Fahrenheit, Ramer, and etc. But Kelvin is the standard in the thermodynamics. So Charles' law states that the volume of the gas is directly proportional to the absolute temperature of the gas, that is V by T is equal to a constant, or implies V2 by V1. All these relations are very important. T2 by T1, T2 and T1 should have to be, precaution is they have to be in Kelvin only if pressure is constant. This is the Charles law 1. There is another law which is also called as the Charles law 2. Charles law 1 is also called as the Gay-Lussac's law, but that name is not that popular. Charles law, one of the Charles laws is also called as the Gay-Lussac's law, but that is not that prominent. We always call it as the Charles law 1, Charles law 2. Charles law 2 states that for a given mass of gas, that is m is equal to constant, volume of the gas remaining constant, volume of the gas remaining constant, pressure of the gas varies directly proportional to the absolute temperature. Absolute temperature means you have to mention only in Kelvin. That is P by T is constant if volume is constant, that is P2 by P1 is equal to T2 by T1. T2 and T1 should have to be in Kelvin only. We have to add the 270, the Kelvin scale, we have to add the 273 to the Celsius to get the Kelvin. That means 0 degrees Celsius is 273 Kelvin, 100 degrees Celsius is 373 Kelvin. The speciality of the Kelvin temperature scale is, there is one important speciality is there. It doesn't have any negative temperatures. Kelvin scale has no negative values. Celsius has negative. You have minus 20 degrees Celsius or minus 30. Supposing if you go to the Kashmir in a peak winter, the temperatures may be around minus 20 or minus 15 degrees Celsius. Okay. So that means negative values are there in Fahrenheit, Ramer and Celsius, but not in Kelvin scale. No negative temperatures. Okay. And in fact, that 0 Kelvin temperature is also very difficult. It's just impossible to reach that 0 Kelvin temperature, which is also called as the absolute zero temperature. Forget about negative. We can't get that absolute zero temperature, that is 0 Kelvin, also in a finite number of operations. That is also called as the third law of thermodynamics, also known as Nernst theorem. See, absolute zero temperature or 0 Kelvin temperature is just impossible to attain in a finite number of operations. We can approach that. We cannot reach that 0 Kelvin temperature. Okay. Because why? Because at that 0 Kelvin, all the activity in the subatomic particles in the molecule also ceases. All the molecular activity just ceases at that 0 Kelvin. So that which is very difficult to achieve. In fact, in a finite number of operations, we cannot reach that 0 Kelvin. That is also called as the third law of thermodynamics. And at that absolute zero temperature, that absolute entropy of the thermodynamic system also approaches 0. The absolute entropy of a perfectly crystalline structured material at absolute zero temperature is 0. That is called as the third law of thermodynamics. Thermodynamics totally there are 4 laws are there. 3 we are very familiar, 0th, 1st and 2nd. There is also third law of thermodynamics which states that at absolute zero temperature, the absolute entropy of a perfectly crystalline structured material approaches 0. As capital T is 0, S is absolute entropy, that also becomes 0. Fine. So, one more precaution here I want to tell here is, we are mentioning about the pressure. We are talking about the pressure in on all these equations, in all these laws. So, how do you define the pressure? It is a normal force per unit area exerted by the fluid molecules on any solid boundary. We are all subjected to the pressure. What pressure? Atmospheric pressure. Outside my body, now there is an atmospheric pressure acting. Inside my body, there is another pressure called as a blood pressure. Inside my body, there is a blood pressure is acting, which is more than the atmospheric pressure. So, right? But whenever you are using the pressure in any thermodynamic problem, when whatever the pressure we are using, it is always the absolute pressure, because in the fluid mechanics also you will see the pressure can be mentioned in as a positive gauge or a negative gauge, which is also called vacuum, or the absolute. But remember, in any thermodynamic problem, the whatever the pressure which you are using, it should be the absolute pressure. I just want to mention that all pressure, all P values that are used in above relations are absolute pressures. How do you get the absolute pressure? Absolute pressure is atmospheric pressure plus gauge pressure. Okay. If it is sometimes that gauge pressure may be negative, sometimes if it is a vacuum also it means negative. Absolute pressure, in case of if the pressure sometimes may be a vacuum, then we have to subtract. We should not add actually. Okay, I would like to mention that in the fluid mechanics also we have to see that if this is atmospheric pressure, if this is the positive gauge, which is any pressure is more than the atmospheric pressure, this is called as the absolute pressure. Sometimes the pressure may be less than the atmospheric pressure, it is called negative gauge. Negative gauge, another name of that is vacuum. So, then the absolute pressure will be absolute pressure, this is absolute pressure. This is absolute zero pressure, this is the absolute zero pressure. All these things you will see again in the fluid mechanics also, in the pressure measurement, in the manometry. Okay. So, this is the absolute pressure here, this is the absolute pressure here. Okay. This is an absolute zero pressure. This line is the absolute zero pressure. Okay. So, fine. So, what I would like to tell is all the pressure values what you are mentioning in any thermodynamic problem, it should be absolute. Now, we have given the Charles law 1 and Charles law 2. Now, I will give the most important law, which is also called as the Avogadro's law. Equal volumes of all gases contain the same number of molecules under the conditions of identical pressures and temperatures. Under the conditions of identical pressures and under the conditions of identical pressures and temperatures. That means if we just take two ideal gases, if the volume is same for both of them, V is same, they are having the same volume, they are subjected to the same pressure, they are reading the same pressure, and temperature also same. Same volume, same pressure, same temperature. In such case, the number of molecules present in those two samples of two different ideal gases also will be the same. There are two samples of ideal gases, having the same volume, having the same pressure, having the same temperature, then the number of molecules contained in those two different samples also will be the same. So, that gases may be, so for example, one is oxygen, one is nitrogen, two different gases, but both are ideal, of course. Then if you ask me what are the examples of ideal gases, there are so many, all the diatomic, monoatomic gases, air, oxygen, nitrogen, helium, all these are can be considered as ideal gases, carbon dioxide, everything, all these gases could be branded as ideal gases. So, equal volumes of all gases contain the same number of molecules under the conditions of identical pressures and temperatures, okay, though the gases are different. Now, I will give the Avogadro's hypothesis. One gram mole of any gas. What do you mean by gram mole? What do you understand by 1 gram mole? If the molecular weight of the gas is expressed in grams, that is called as a gram mole, simply known as mole. 1 mole or 1 gram mole both mean the same. What is actually meant by 1 gram mole? If you just express the molecular weight of any gas in grams, say for example oxygen is there. What is the molecular weight of oxygen? 32. That is 32 grams of oxygen is 1 gram mole of oxygen or 1 mole of oxygen. Gram mole or mole both mean the same. For example, if you take nitrogen, what is the molecular weight of nitrogen? 28. 28 grams of nitrogen is the 1 gram mole of nitrogen or 1 mole of nitrogen. 1 gram mole of any ideal gas, maybe air or oxygen, nitrogen, hydrogen, helium, carbon dioxide, all these are can be branded, can be treated as ideal gases. 1 gram mole of any gas contain Avogadro's number of molecules at normal temperature and pressure. What is the normal temperature and pressure? 0 degrees Celsius or 273 Kelvin and 101.3 kilopascal. They are termed as the normal temperature and pressure. Generally in 11th class, 12th class you might have studied STP, standard temperature, but leave that. In engineering we always talk about NTP, normal temperature and pressure, which are considered as 0 degrees Celsius or 273 Kelvin and 101.3 kilopascal absolute, NTP conditions. They are 0 Celsius and 101.3 kilopascal. At NTP, 1 gram mole of contain Avogadro's number of molecules and occupy a volume of 22.4 liters. So, this is also called as an Avogadro's hypothesis. Okay. What is Avogadro's number actually? You must have given 6.0 to 3 into 10 to the power of 28. No, that is the Avogadro's number. We don't want to go into the details of that Avogadro's number. Just remember that statement, which is also obeyed by the ideal gas. I have stated until now 4 laws, right? Avogadro's law, Boyle's law, Charles law 1, Charles law 2. Any gas which obeys all these gas laws at all pressures and temperatures is called as the ideal gas. Of course, there are two more laws also there. They will also state them. It is called as a Dalton's law of partial pressures and Avogadro's law of partial volumes. In fact, those two laws, Dalton's law of partial pressures and Avogadro's law of partial volumes, they talk about mixtures of ideal gases. For example, if you take air, is the air compound or a mixture? Means air is a mixture. Mixture of what? Mixture of nitrogen and oxygen. Dominating portion, dominating mass is nitrogen and lesser mass is oxygen. Air is a mixture of nitrogen and oxygen, what we are breathing. Okay. Some of you may be asking what is 1 gram mole. I just try to you write it. 1 gram mole means 1 gram mole or mole means molecular weight of gas expressed in grams. For example I am giving 28 grams of nitrogen, 28 is the molecular weight of nitrogen, is 1 mole. 1 mole or gram mole both mean the same, 1 mole of nitrogen. 32 grams of oxygen is 1 mole of oxygen. Third example, 29 grams of air, 29 is the molecular weight of air, 29 grams of air is 1 mole of air. Okay. So, just express the molecular weight in grams, that becomes a gram mole. If you express the molecular weight in kg, it becomes kg mole, that is it. Okay. 1 kg mole means you have to express the molecular weight, you just have to keep the kg besides that, right. Now, we understood that, now I am going to state having understood all these laws, now I am going to state the Dalton's law of partial pressures. It is regarding the gaseous mixture. Dalton's law of partial pressures. Regarding gaseous mixtures, this is not a single gas, it is now you have got a multiples of gases as a mixture. Regarding gas mixture, ideal gas mixture, obviously it is an ideal gas. When you have a mixture of two different ideal gases, that mixture also will become an ideal. For example, nitrogen is their ideal gas, oxygen is their ideal gas. The mixture of them, air, it is an ideal gas, obviously. So, Dalton's law of partial pressures, it is stated like this. Supposing you have a mixture of two different gases, A plus B. It is a mixture, two different gases, both A and B are ideal. Now, the combinedly, when they are existing as a mixture, combinedly they are existing as a pressure of the mixture. They are indicating some pressure. You know, the pressure is nothing but normal force per unit area exerted by the fluid on its solid boundary. What are the units of pressure? Newton per meter square. Units of pressure are Newton per meter square, 1 Pascal. 1 Pascal is the 1 Newton per meter square, which is a fundamental unit of pressure in our SI system. We always follow the SI system. Pressure units are Newton per meter square. 1 atmospheric pressure surrounding us is approximately equal to the 101 kilopascal. You can take it as 100, sometimes they take it as 100, but usually more correctly it is 101.3 kilopascal, standard atmospheric pressure. Okay, it means level. Fine. 1 bar is again equal to the 10 to the power of 5 pascals. Pressure is the units are pascals in SI system. So, we have got two mixtures, two gases existing as a mixture, exerting a pressure of the mixture actually, and having a volume V, certain temperature T. this law states that if gas A alone exerts in the same volume, A alone, B is not there. A alone, the same A alone had been there in the same volume, and at the same temperature, Please note that in all the thermodynamic problems, try to substitute the temperature values only in Kelvin. Never put it in Celsius. Add always 273 wherever you are doing a thermodynamic problem. Okay, and B alone, if it exerts, if it is there in the same volume, if A alone is there, how much pressure is exerting? That is PA. Pressure gauge is indicating PA. If B alone is there in the same volume, supposing I just asked all the molecules of A only to get out, only molecules of A I get out. No, only B will be left over there. So, how much pressure that B will be showing? It is PB. Okay, in the same volume, at the same temperature T Kelvin. Okay. Then this Dalton's law of total partial pressure states that the total pressure exerted by the mixture, is the sum of partial pressure of A plus partial pressure of B. So, the law states that the total pressure exerted by a mixture of gases, that holds good for all the, there may be 3 gases also, same law holds good. I have considered here only 2, but there may be 3 or 4 gases also. The total pressure exerted by a mixture of gases is the sum of its partial pressures. That is pressure of the mixture A plus B is equal to PA plus PB. That is called as the Dalton's law. Provided all the gases A and B must be ideal. Dalton's law also hold good only for the ideal gases like air. Okay. Please note that what is that partial pressure meaning? Partial pressure meaning means only that gas alone should be there in the same volume at the same temperature, that conditions. The same volume at the same temperature, that gas alone should be there, that pressure, how much pressure it will exert. I am writing here, partial pressure is the pressure exerted by partial pressure of a gas is the pressure exerted by that gas alone. That gas alone is present in the same volume. And same temperature, the same volume and at same temperature, the same volume and at the same temperature as that of mixture. Whatever the pressure and whatever the volume occupied by the mixture, same volume should be there. Whatever the volume of the mixture, same volume should be there for the B also actually. So, B alone must be there. then the pressure exerted alone by that gas alone is called as the partial pressure of P. Dalton's law says that P of the mixture is the sum of PA plus PB. This is the Dalton's law of partial pressures. Now I am going to state the Dalton's law of Avogadro's law of partial volumes. That is also regarding the mixture. Avogadro's law of partial volumes. Suppose that there is a mixture A plus B. It is exerting some pressure of the mixture, it is occupying some volume and at a temperature T Kelvin. There is a mixture. Dalton's law and Avogadro's law are regarding to the mixtures of ideal gases. There is two gases A and B are existing as a mixture, exerting a pressure P of the mixture, occupying a volume V and at a temperature of T Kelvin. Then I am defining partial volume. Earlier I have defined the partial pressure. What is a partial volume? Partial volume means if that A alone, if A alone is there at the same temperature, exerting the same pressure as that of the mixture. Pressure of the mixture is equal to the pressure of the mixture, but A alone how it is exerting, A alone it is exerting, and how much volume it is occupies. This volume is the partial volume of A. And what is the partial volume of B? If B alone is there at the same temperature, and what is the pressure exerted by that B alone should be that whatever the pressure of the mixture, all pressures are same. The pressure of the mixture, pressure exerted by A, how much would be the volume, that is called as the V partial of B alone, partial volume of B. Partial volume of B means if B alone is there exerting the same total pressure as that of the mixture, but at the same temperature, then this Avogadro's law states that the total volume occupied by a mixture of ideal gases must be equal to the sum of its partial volumes. Must be equal to the sum of the partial volumes of the gases. Sum of the partial volumes of individual gases. I think what do you mean by partial volume? It should that gas should exert the same pressure. It should be at the same temperature as that of the mixture. But that gas alone should be there. Then the volume occupied by that gas A alone is called as the partial volume of A, and this is a partial volume of B. That means volume of the mixture is the partial volume of A plus partial volume of B. I hope you understood what is the meaning of the partial value. Partial value means the gas alone should be there, it should have the same pressure as that of the mixture. See that in all these cases the pressure of the mixture, and here the pressure of the mixture, here the pressure of the mixture. So any gas which obeys all these above gas laws is called as an ideal gas. Okay. Now I'll derive the ideal gas equation. Boyle's law states the P is directly proportional to the 1 by V. Charles' law states that P is directly proportional to the absolute temperature. Of course, T means, I already mentioned T in Kelvin. We have to add the 273 to the Celsius. Always, all the problems of thermodynamics by default, blindly add the 273 to the Celsius if it is given to Celsius. Sometimes if it is given directly in Kelvin, don't add anything. So be careful about the data. If the temperatures are directly given in Kelvin, don't add anything, right? Then you have got the Avogadro's law. At a given pressure, and temperature, the volume of the gas is directly proportional to the N, where N is the number of moles. N is the number of moles. How did you define the number of moles? N is equal to mass divided by molecular weight. That is the number of moles. Okay. By combining these three, by combining all the above, PV, right? PV is directly proportional to the N into T. The proportionality constant is only known as universal gas constant. The proportionality constant is known as the universal gas constant. This is the most famously known as ideal gas equation, also known as the perfect gas equation, where this R is two lines I am putting to avoid the confusion between. There is one more R I will bring in. There is one more R I will get in, that is called as the characteristic gas constant. This is called as the universal gas constant. Universal gas constant, its value is 8.314 kilojoule per kg mole Kelvin. This is a very standard value. You have to remember this value, 8.314 kilojoule per kg mole Kelvin. That is same for all the gases. I mean to say, universal gas constant, R is same. Universal gas constant is same for all the gases. Its units are kilojoule per kg mole Kelvin. But when you write this PV is equal to, nRT, one precaution is always keep this in kilopascal, that too in absolute. I already mentioned, never use the gauge pressure in any thermodynamic problems. Gauge business was only in the FM. Positive gauge or a negative gauge or vacuum, they are all they are all in the pertaining to the fluid mechanics. But when you come to the thermodynamics, when you talk about the thermodynamics, when you are doing the problems of thermodynamics, always keep the pressure only in absolute, that too in this equation particularly kilopascal. This N is the number of moles, the T obviously already given in Kelvin. This should be kept, then it should be in kilojoule per kg mole Kelvin. Volume of, you know well, that is should be in meter cube, never in liters like that. So these are the N is the number of moles, that is. So this is the ideal gas equation or perfect gas equation. Any gas which obeys this equation, at all pressures and temperatures can be branded as ideal gas, also known as perfect gas. Okay, this is an ideal gas equation in the molar form actually, but on mass basis, the same equation can be written in a different way. But on mass basis, this is on the mole basis. But on mass basis, ideal gas or perfect gas equation, ideal gas and perfect gas both mean the same. Two names, ideal gas and perfect gas is, it can be written as PV is equal to MRT. I am not keeping the two lines. When I keep the two lines like this, some of the books will use capital R for the universal gas constant and small r for the, this R is called as the characteristic gas constant. Here this mass should be in kg. Here N is the, what is N here? N is the number of moles already. PV is equal to nRT, PV is equal to mRT. But this R is different. Here R is called as the characteristic gas constant. Why it is called as a characteristic gas constant? Since it is different for different gases. It is different for different gases. For air it is different, for oxygen is different, for nitrogen it is different. It is different for, that is why it is called as it is a character of a gas. That is why it is called as the characteristic gas constant. Okay. M is the kg. Here N is the number of, here the N is the number of moles there. Here M is in kg. You should observe the difference there. So for example, I am giving, for example, R of air, the most standard ideal gas which you do in the problems, it is 0.287. Units are also different. Its units are kilojoule per kg Kelvin. You can see, whereas R units are kilojoule per kg mole Kelvin, here it is kilojoule per kg Kelvin. Pressure always prefer to mention only in kilopascal. So these two are the two different forms of the same equation, but one on the mole basis or one other on the mass basis. Okay, that R is different, this R is different. This is a universal gas constant, this is a characteristic gas constant, but there is a relation between them. This R of any gas could be easily obtained by dividing the universal gas constant with the molecular weight of the gas. For example, R of air I require. Universal gas constant is the same for all the gases, that is why it is called universal. 8.314, just divide with molecular weight of the air, that is 29. You will exactly get 0.287 kilojoule per. Like that you can get the characteristic gas constant of any gas, which what we need is just you need to know the molecular weight of the gas. So examples of ideal gases, if we just ask me, What are the various ideal gases? Oxygen, nitrogen, air. Air is a mixture of nitrogen and oxygen. Helium, hydrogen, carbon dioxide, highly superheated steam, even the highly superheated, not wet steam, highly superheated steam, what is the formula of the superheated steam? H2O super H2O. All these can be taken as, ideal gas. Can be approximate. Actually, precisely speaking, no gas is perfect or no gas is ideal. But we approximate all these gases as almost ideal. They almost follow that PV is equal to nRT almost at all the normal engineering pressures and temperatures. They all obey that PV is equal to nRT. So all these gases O2, N2, air, etc., can be branded as ideal gases because they obey that PV is equal to nRT. Fine. So, okay, the gas which does not obey that ideal gas equation is called as a real gas. At all pressures and temperatures, it does not obey that, it is called as a real gas actually. Okay. There is a difference between the real gas behavior and ideal gas behavior. Which does not obey all the gas laws or PV is equal to nRT at all pressures and temperatures is called real gas. But there is one concession. There is one concession here. A real gas would almost behave like ideal gas at very low pressures and at very high temperatures. At very low pressures and at very high temperatures, real gas behavior and ideal gas behavior almost behave like in the similar manner. They become identical. There is one slight concession, but very important note. But at very low pressures, that is as P tends to 0, and also at very high temperatures, that is as T tends to infinity. But at very low pressures, as P tends to 0 and T tends to infinity, real gas almost behaves like ideal gas. That means ideal gas and real gas behavior become same. If P tends to 0, high vacuums at very low pressures or high vacuums also. We can also say this as high vacuums. P tends to 0 means high vacuums, you can say. Actually, there is one another important theory you have learnt in physics also, kinetic theory of gases. There is a kinetic theory interpretation of the ideal gas is there. According to that kinetic theory of ideal gas behavior, the molecules of the ideal gas do not have any volume, but they have the mass. The molecules of the ideal gas do not have any volume, but they possess mass. That is why they are called as the point masses. According to the kinetic theory postulates of the ideal gas, we just say kinetic theory interpretation. Kinetic theory interpretation. kinetic theory if you see the molecules of ideal gas have no volume but they have mass. That is why they are called point masses. Number 2, there are no intermolecular attractive forces, intermolecular attractive or repulsive forces or repulsive. They don't attract, they don't repulse. There are no intermolecular forces of attraction or repulsion among the molecules. That is number 3. All the collisions all the intermolecular collisions among the molecules are perfectly elastic That is, there is no loss of energy. What is the elastic collision nature? Both momentum and kinetic energy both are conserved. So no loss of energy during the collision. So there are some other assumptions are also there. These are the main assumptions. So based on the kinetic theory interpretation, so hence based on kinetic theory, based on kinetic theory, for ideal gas we may write as PV is equal to 1/3 mc square. We can also write where c bar is the RMS velocity of gas molecule. Root means square velocity. RMS velocity of gas molecule. Root means square velocity they call. But we already deduced that PV is equal to MRT, right? We already know. That means by combining these two, this is equation 1, this is equation 2. If you combine these two, combining 1 and 2, C bar is directly proportional to the square root of the absolute temperature. That means the average kinetic energy of the ideal gas molecule is directly proportional to the absolute temperature of the gas. Hence, I can say, the average kinetic energy of ideal gas molecule is directly proportional to absolute temperature of gas. Here comes the very striking important definition of the ideal gas. Very important striking feature of ideal gas you can see here. Later I am going to define one important property called internal energy, very fundamental property in thermodynamics. Internal energy of ideal gas depends only on the temperature of the gas according to this equation. According to this equation, the internal energy of ideal gas depends only on the temperature. What is an internal energy of ideal gas? The sum of all the translational kinetic energies of all the molecules. It is a stored form of energy. Energy can be stored inside the system in the form of internal energy. Neglecting the velocity of the system, neglecting the gravity, neglecting the gravitational weight of the system, the energy can be stored inside the thermodynamic system in the form of the internal energy, which is nothing but the sum of all the forms of molecular energies. Okay, so the internal energy of ideal gas, which is the sum of all the kinetic energies of all the molecules moving inside the system, depends only on the temperature of the gas, because the kinetic energy of the gas of molecule and the temperature are correlated or linked by the kinetic theory interpretation of the ideal gas. Kinetic theory interpretation, kinetic theory modeling of ideal gas, kinetic theory interpretation of ideal gas tells that root mean square velocity, RMS velocity of the gas molecule, RMS velocity of the gas molecule is directly proportional to the absolute temperature of the gas. And from that we can say that the average kinetic energy of the gas molecule depends only on the temperature of the gas. And if you add up all the molecular kinetic energies, what we get? The internal energy of the gas. That means the internal energy of the gas is directly proportional to the temperature of the gas. Very striking, important law, which is also called as the Joule's law of ideal gas. This is forms the basis of the Joule's law of ideal gas. Hence, it can be stated that the internal energy. Now later I will define what is an internal energy. Internal energy is the outcome of the first law of thermodynamics. The internal energy of ideal gas, which is generally denoted with U. Depends only on the temperature of gas. This is called Joule's law of ideal gas. Remember that. This is called Joule's law. U is a function of T only for ideal gas. Later we are going to see that this specific internal energy is hence kilojoule per kg. What is this U? Small u, specific internal energy. This is the specific, Cv is the specific heat at constant volume of gas. So this is the basis for the Joule's law of ideal gas. From kinetic theory also we can come to the Joule's law. Later we are going to see that not only the internal energy, but also the enthalpy of ideal gas. I am stating here also the enthalpy of ideal gas also depends only on the temperature. H is the enthalpy, but here H could be written as Cp into T. What is that small h? This is the specific, this is specific internal energy, this is specific enthalpy. This is specific internal energy, this is the specific enthalpy. Cp is the these are all the very important relation in thermodynamics. Specific heat at constant pressure. I am giving the very important relation. H is equal to 4, H is a function of temperature only. For ideal gas. But for real gas, both internal energy and enthalpy depends not only on the temperature but also on the pressure. Real gas obeys a different form of equation called as the van der Waals equation of state, that I will state later. First let me focus on the important thermodynamic fluid which is called as an ideal gas. Okay. So, the main important thermodynamic fluid which I am discussing now, it is an ideal gas, which is mostly air in the problems of thermodynamics. Okay. Any doubts? Actually, I would like to announce that while I am covering this subject, purely keeping in point of your examination for the KTU, all these video lectures are aimed at making the students thorough just to face this KTU examination. Okay, in these 3 days I would like to, because 3 days, tomorrow and after tomorrow, I would like to cover as much as possible thermodynamics, keeping how to score more in the KTU examination. Though the student is not prepared much in the thermodynamics, only that is my objective of these video lectures. If the students get any doubts, please, we are putting on link there in the comment box. There you can check, you can post your doubts. I personally will be clearing the doubts. And also, apart from not this link, there are some other mechanical engineering community groups are there. So you can log into, you can connect into that links also, you can join, because I will be covering all the subjects, not only thermodynamics. Every subject I will be covering, I will be clearing the doubts. If not me, some other faculty of our team. We have a team here, mechanical engineering team, but most of the doubts will be cleared by me. This is Sekhar from Msigma. So take a break for about 5 to 10 minutes. Break you can take. After the break, we'll continue. doubts for phone. I'm not saying that. Anyhow, doubts you are mentioning. I keep mentioning that. Well, welcome back to the class. In fact, I had come to a very important striking point regarding the ideal gas behavior. For ideal gas, not only the internal energy but also the enthalpy of the ideal gas depends only on the temperature of the gas. Whereas for the real gas, internal energy and enthalpy, they not only depend on the temperature but also depend upon the pressure. So that is a very important point you always keep in mind. The internal energy changes of the ideal gas are proportional to the temperature changes. I am just writing that in the equation form. Therefore, for any ideal gas, during any thermodynamic process, change in internal energy, delta is the symbol used for the change. Change in internal energy of the ideal gas is mCV delta T kilojoules and delta H mCp delta T. So these are the very striking points you have to keep in mind. CV and CP are the specific heats at constant volume and specific heat at constant pressure. Okay. Whereas for real gas, internal energy depends not only on the temperature but also on the pressure. Whereas for the real gas, what is a real gas? Which does not obey all the gas laws at all pressures and temperatures. Enthalpy also depends not only on the temperature but also on the pressure. These are for the real gas. These are for the ideal gas. Okay, real gas obeys different kind of equation which is called as the van der Waals equation of state, which I will highlight later. So now, having talked about the specific heats Cp and Cv, now I am going to give the clear definitions of Cp and Cv. You see, these points may not be highlighted by your respective teachers in your colleges, maybe a private college or a government college, because with all my vast experience of more than 30 years, actually I have got a huge experience of around 30 years in all these subjects. I have seen so many of my students have become the lecturers in so many engineering colleges across India, actually I can say. Because I have produced the single digit rankers of GATE across India earlier with all my experience. I am saying that even the college lecturers also, government college lecturers also, I observed that they are giving the wrong inputs to the students. They are not able to teach the students in a sequential manner how to present that concepts well in the examination. Because earlier also I have seen, but 1 year ago, actually when a student from the College of Engineering Trivandrum has come to me, sir, I am getting the lesser marks in the thermodynamics and some of the papers I was not able to clear. And I had told them some sequence of notes. Some within 2 hours I had given him the guidance. This way you present this, in this way, in this direction you write the paper. Then later he called me that, sir, many thanks for your guidance. I am able to clear the exam. I am able to score very good marks in that thermodynamics and fluid mechanics as well. So the presentation of the student in the examination is very much crucial, because in the valuation, while doing the valuation, valuer will not have that much time, because I also did so many valuations in my spot valuation in the university. Evaluator, while you are correcting your final paper examination, awarding the marks, you will not get that much time. See, you will spare oddly 5 maximum, he is given a 15 minutes time for each paper, not more than that. 10 to 15 minutes. In that 15 minutes, he has to see that all the questions what you have written. The way you present is very much important. So if you go through my notes of this thermodynamics, definitely you would be able to write that concept, you would be able to attempt the question, whatever there it is given. The moment you read the question paper, you will be able to connect that particular question immediately to my notes. If you have gone through these my notes as well, if you whatever the teaching I am giving now, if you thoroughly follow this sequence of the subject, the moment you read the question in the examination, you will be immediately connect to that particular point of my notes, and you would be able to present them very clearly with the assumptions. So, in the university examination, how you present the paper is, how you present your answer to the question is very, very important, unlike the GATE and IES. See, they are the different, because you are put a B, C, D. So, but in the KTU papers, how you write, write the assumptions, give a figure, give a problem, write the assumptions, what process is that, what are the assumptions, why so and so equation you are applying. So, all these assumptions, all these correlations, if you connect it well in the presentation of the answer, definitely you can score very good marks in all these subjects like thermodynamics, heat transfer or fluid mechanics, because these are all the analysis based subject. We have to write the considerations or assumptions, you have to give a figure, and at the end of the problem you have to give some analysis of the result also. If you write, the evaluator will be terribly impressed. In fact, I have seen many teachers will learn some new points from by seeing your good students' answers, because teachers are not that up to date, because thanks to so many dumping of engineering colleges, I have seen that when the teachers are also not able to give the clear concepts in the paper, in the classrooms as such. So, how come the students you expect the get the knowledge? So, what I am to fill that gaps, we are here. To fill that gaps, to fill that blocks of preparation, we are here because of all our experience. The way I am teaching you the sequence of the subject, and you would be able to write the paper very, very well in the examination, I hope, if you follow thoroughly and get your doubts clarified through WhatsApp groups or whatever it is. Okay. So, presentation skill you have to develop, okay, and writing the assumptions. So, no, you will come to see in my due course of coverage of the syllabus, you will come to see all that how I am presenting the subject, and in the similar way you can prepare and give the examination well and aim for the very good marks. And coming to that point of specific heats, I am going to define the very important definition in thermodynamics, specific heats of gas. All the solids and liquids, all this, take water, take steel, take copper, all the solids, all the liquids will have only one specific heat. Only gases and vapors will have two specific heats, Cp and Cv. Why so? Why so? Because the reason is this: when you are heating the water, how do you define the specific heat? For a unit mass of the substance, for a 1 degree Celsius rise in temperature, how much heat is required? That is called as, after all, specific heat you have been learning since 11th class. For unit mass of the substance, for 1 degree Celsius rise in temperature, or 1 kg or unit mass of the substance, 1 degree Celsius rise in temperature, how much heat is required? That is a specific heat. That is as far as the solids, liquids, the definition is very, very clear. But when you come to the gas, when you are heating the gas, it's liable to change in volume. Its pressure is likely to change, temperature is also likely to change. If you allow the gas to expand, its volume also will increase. Gases behave in a different manner as compared to the solids and liquids. When you are heating a gas, air, its volume is likely to increase, its pressure is also likely to increase, its temperature is also likely to increase. So, that is why for gases we have to define two specific heats. Okay, keeping one parameter constant. If you keep the volume constant, that specific heat is called as a specific heat at constant volume. If you keep the pressure, maintain the pressure of the gas constant, if you supplying the heat and how much heat is required for 1 degree Celsius rise in temperature, it is a Cp. So, I hope you understood why the gases require two specific heats, because when you are heating the gas, not only the temperature, but its pressure would likely to increase, its volume also would like to increase, because gas likely to expand under heating. Whereas if you are heating the water, but does it expand with heating? Never. Suppose you are heating the milk, will it, as you are increasing the temperature of the milk, will it come out of the vessel immediately? No, simply temperature will be increasing. But air is not like that. So when you are heating the air, it would like to expand, change its volume, change its pressure also. So I maintain one parameter constant and see the change, how much heat is required for 1 degree Celsius rise in temperature. Specific heats of a gas could be defined like this: Cp, specific heat at constant volume. It is also called, denoted as Cv. It is the amount of heat required to increase the temperature of unit mass of gas. Unit mass means 1 kg through 1 degree Celsius at constant volume, keeping the volume constant. It could be understood from this figure like this. Now I have taken the gas 1 kg air, maybe gas means air. I have taken in a rigid container, a rigid vessel, rigid container. Why rigid container? I want to maintain the gas constant, right? Gas volume constant. Because as I am supplying the heat, the gas is liable to increase. It would like to expand. Any gas, when you are heating it, it would like to expand. Liquids and solids also expand, but the expansion is very, 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 very small, minute. We can't see that. But gas clearly expands more. Okay, as the temperature of the gas is expanding, as increasing, as you are heating the gas, it would like to expand. So, 1 degree Celsius rise in temperature I want to have. 1 kg mass of the air or any gas, 1 degree Celsius rise in temperature, keeping the volume constant, that heat required is the Cv. This is the Cv, kilojoules per kg per Kelvin. Somebody asked, you are telling 1 degree Celsius rise in temperature, delta means what? Change in temperature. If you take 25, how much heat is required to get it 26? If you take at 15 degrees Celsius, how much heat is required to make it 16, 15 to 16? Then 1 degree Celsius rise in temperature, you are telling, some students ask me, then in the units you are writing per Kelvin, what is that? Means this is the thing, change in temperature is same in Celsius scale and Kelvin scale. 1 degree Celsius rise in temperature is equal to 1 Kelvin rise in temperature. Base is different. Whatever the delta T in Celsius scale, same is the delta T in Kelvin scale. 0 degree Celsius to 1 degree Celsius, that is the rise in temperature in Celsius scale. Corresponding to 0 degree Celsius, how much? 273. Corresponding to 1 degree Celsius, how much Kelvin? 274. So again 1 Kelvin rise in temperature. So that is why units of Cv will be kilojoule per kg Kelvin. So it is the amount of heat required to increase the temperature of unit mass of gas through 1 degree Celsius at constant volume, right? I am giving the Cv of air because air is the most commonly used ideal gas in the future subjects also. Later in thermal engineering, etc. also, air only you will come across mostly, thermodynamic fluid. So better to remember that. 0.718 kilojoule per kg Kelvin, only for air, this value. Okay. Then I will define the Cp. Specific heat at constant pressure. Cp. Cp is defined as the amount of heat required to increase the temperature of unit mass of gas through 1 degree Celsius at constant pressure. You want to maintain the pressure constant, and then increase the temperature. In the earlier case, we have maintained the volume constant. So, when you want to maintain the pressure constant while increasing the temperature, you have to allow the gas to expand. See, I already said, whenever you are increasing the temperature, whenever trying supplying the heat, gas is liable to increase its volume. But in the earlier case, we have taken a rigid vessel. Gas is not able to expand. But that time, and in the earlier case, if we just see here, in the earlier case, definitely along with the temperature, pressure will increase. Here, delta P, along with when the temperature is increasing, because you are taking in a constant volume, pressure also will increase. But now I want to maintain the pressure constant. Then can you take it in a rigid vessel? No. You have to allow the gas to expand. How can you maintain the pressure constant while supplying heat? We have to allow the gas to expand. For that, I have taken the gas in a piston cylinder arrangement like this. This is the piston cylinder arrangement. I have taken 1 kg gas. Air, you can take, for example, most commonly used ideal gas or working fluid is air. That is why later we are going to see air standard cycles. Working fluid is air, 1 kg air, you can approximate, you can assume. Temperature rise, I would like to have 1 degree Celsius or 1 Kelvin. You are supplying the heat. Okay, I want to increase the temperature just by 1 degree Celsius. Because you are allowing the gas to expand, the pressure is automatically maintained constant. Work is performed by the gas on the atmosphere. Because as the gas is expanding, work is performed by the air on the surroundings, right? Because you are allowing the gas to expand, but the pressure is maintained constant. So that heat required is called as the Cp, units kilojoule per kg Kelvin. So this is the definition of the Cp. Okay, amount of heat required to increase the temperature of unit mass of the substance through 1 degree Celsius, maintaining the pressure constant. Cp for any gas, Cp is always greater than Cv. Why? Such questions may come in the exam. Why Cp is always greater than Cv? Can you think of that? The answer is there very much in the figure itself. If you just observe the constant volume heating and constant pressure heating, that the figures itself tell the answer. Cp is more because of is greater than Cv because if you just look at the constant volume heating, do you have any work performed by the gas here? No. Whatever the heat you are supplying, that is solely and wholly taken by, absorbed by the gas for increasing its temperature. Whereas when you look at the constant pressure heating, the heat you are supplying to the gas is being utilized in two different ways. One way is to increase the temperature, it is being utilized. Another, some amount of the heat is used for doing work. You are getting work here, expansion work. How that work is coming? Because you are supplying the heat. A part of the heat supplied to the gas is utilized to do that work. Only the remaining part will be going for increasing the temperature. In both the cases, same gas, same delta T, same temperature change, same mass, same gas, but you require more heat here. Why more heat here? Because a part of the heat supplied to the gas is being utilized to do external work. In the earlier case, there was no work. There was no expansion work because it is a constant volume. Whatever the heat you are giving, everything is swallowed by the gas for rising its temperature in constant volume case. So because I am writing the reason here, because in constant pressure heating, the heat supplied to the gas is simultaneously being used for raising the temperature and also for doing external work. You are clearly seeing here gas is expanding, whereas in constant volume heating the heat supplied to the gas is entirely being used is totally entirely being used for raising the temperature alone. For raising the temperature alone. That is why Cp for any gas Cp is always greater than Cv. This ratio for any gas Cp by Cv is greater than 1 because this ratio is famously known as adiabatic index. Adiabatic index of gas. Why it is called adiabatic? Because the equation of that adiabatic thermodynamic process contains this Pv to the power of gamma is equal to constant. That is why this gamma is called as an adiabatic index. It varies with atomicity. So if you look at this, actually gamma is equal to 1.66 for monoatomic gases. Mono means one molecule contains one atom, like helium, neon, noble gases. We also call it as noble gases or inert gases. The last column of the periodic table. Gamma is equal to 1.4. This is the range you have to remember. For most of our gases, what we see in our problems are diatomic in nature. Diatomic means one molecule contains two atoms, O2, N2, and air, and hydrogen, etc. Gamma is equal to 1.33 for polyatomic or more than 2 for polyatomic gases. Like carbon dioxide, etc. So as the atomicity is increasing, gamma value is decreasing. We can see, but most of the range is this range we have to remember. No air, this is the range generally. But helium and monoatomic, they have the 1.66. Ratio is greater than 1. The difference, if you see, Cp minus Cv is equal to characteristic gas constant. Please remember these two relations. The difference of the specific heats is the characteristic gas constant, kilojoule per kg Kelvin. I forgot to give the Cp value for the air. I am just giving that. Cp of the air, Cv of the air I had given. Cp of the air will be 1.005 kilojoule per kg. Please remember these values. For air, remember the R value, Cp value, Cv value. Because very often, very frequently, we need to use them. For air, I am just writing this. Example, 1.005 minus 0.717 or 0.718, that comes to around 0.287. These are the values we write for the air, 1.005, all are having the same units there. So by combining this relation and this relation, we will get, now we get Cp is equal to gamma by gamma minus 1 into R, and Cv is equal to R by gamma minus 1. Please remember these values because we will be using the very often. Please note that this R in these relations, R is a characteristic gas constant. So for any gas, take for any gas, say for example, say nitrogen. I take the example of nitrogen. If you just give me the molecular weight, I can find out all the things from these relations. I'll do one problem here. For example, say for nitrogen gas, whose molecular weight is 28. Right? Only I just know the atomic weight is 14. 2 into 14 is 28 is the molecular weight. Now the characteristic gas constant, this R is the characteristic gas constant, right? This is which could be obtained as we know that universal gas constant divided by molecular weight, that is 8.314, which is same for all the gases. This double line I am using, this is a double line I am using for the universal gas constant divided by molecular weight is 28, right? So we will get the characteristic gas constant, which is characteristic means it is different for different gases. Capital R, this double R, double line R is universal. This is universal gas constant because this is same for all the gases, but molecular weight is different for different gases. Therefore, characteristic gas constant will be different for different gases. There here nitrogen, I got it. Now, for example, nitrogen is a diatomic or monatomic? Diatomic. Diatomic means what is the gamma value? 1.4. That is an adiabatic index. Therefore, I can get the Cp of nitrogen, for example, if nitrogen gas, if you want to get gamma is 1.4. Why 1.4? It is a diatomic. Divided by 1.4 minus 1 into 8.314 divided by 28. That gives the Cp of nitrogen. And if you want to write the CV of nitrogen gas, that is 8.314 divided by 28 R by gamma minus 1, that is R by gamma, that is it becomes 0.4, 1.4 minus 1, it becomes 0.4 kilojoule per kg Kelvin. So for any gas, if you just you are given the molecular weight, you can find out all the things, characteristic gas constant, Cp, Cv, everything we could find out. The difference of the specific heat is, or the ratio of the specific heat is gamma. Okay. So now we have come across the I covered the very fundamental module of the thermodynamic problem, identifying the working fluid and finding out all its characteristics. If the working fluid is ideal gas, then somebody may get a doubt. If the working fluid is not ideal gas, say we discussed about what are the ideal gases, then what is not ideal gas? And then I tell you example in our thermal engineering, steam is not ideal gas. A wet steam is there. In your cooker there is a wet steam. Steam is boiling, okay, so a whistle will rise, steam is released. It is a steam inside a cooker. Is it an ideal gas? It is a vapor, definitely. That is why steam is released. It is not ideal gas. I can say it is not ideal. Refrigerant in your refrigerator is circulating, refrigerant in the pipes, the evaporator and condenser pipes. It is not ideal gas. We can't write these relations there. PV is equal to nRT, we can't write. So they are not. So how to solve them? That we have got a different chapter later called as the pure substances, properties of pure substances, where I discuss saturated liquid, saturated vapor, Dreyfus fraction, etc. So for them, all these relations will not be valid. This is only for the ideal gas. One particular important kind of thermodynamic fluid, steam, refrigerant, they all come under a different category. They are not ideal gas. They don't obey this. So having done this important thermodynamic fluid, now I will go to the second important inquiry. I already said 3 inquiries you have to make. 3 inquiries you have to make while you are attempting the thermodynamic problem. Nature of the working fluid, we got it. Second inquiry is what? Nature of the system. Now I will define the very important definition called as the thermodynamic system. See, the sequence which I am teaching is out of my vast experience. Your sequence of coverage in the class may be different, but in this sequence if you follow, things will become easy, and whatever the question is given you will be able to write. Okay, you can present the answer well and to score the best marks in the semester examinations. What is a thermodynamic system? Thermodynamic system is a fixed region in space upon which our attention is concentrated or focused for thermodynamic study. So, you want to make a thermodynamic analysis. What do you mean by thermodynamic analysis? How much heat interaction is, how much heat is going into the system, how much heat is rejected by the system, how much work is done by the system. Are you doing any work or are you getting any work? Is it an expansion work or a compression work? Or what are the changes in the properties of the system? Is the pressure is increasing or temperature is increasing or volume is increasing? So, to do all this analysis, we have to take some fixed region in space. On that your focus is done. Your focus is mainly pointed out to that particular region considered in the space. Now I am writing the definition. It is a fixed region in space upon which our attention is concentrated or focused for thermodynamic study or analysis. Thermodynamic analysis means, after all, thermodynamics is the subject of two basic energies, heat energy and work energy. Thermo is connected with heat, dynamics is connected with work, right? This is the system. You can fix the boundary anywhere as you wish. This is the thermodynamic system, and this is the boundary of the system. Purely arbitrary. Where you keep the boundary, it is up to your wish, your will and wish. System, this is the boundary. Everything external to the boundary is called as the surroundings. This is the system, surroundings, boundary. System and surroundings are separated by the boundary. Boundary can move. Boundary can deform. Need not be that. As during the process, boundary can move, change its shape. I mean to say that boundary can change its shape. Between the system and the surroundings, that there is an energy interaction. Heat may enter and work may leave. Work may be done by the system, or sometimes heat may be rejected. Q is a standard symbol for heat, and work may be done on the system. Anyway, it can happen. So, between the system and surroundings, there is an energy interaction, either in the form of heat, or in the form of work. Either in the form of heat or in the form of work, there may be energy interaction. As a result of that interaction, the properties of the system may change. Pressure, volume, temperature, all of them change. Some of them can remain constant like that. Okay, this is a basic definition of the thermodynamics. You want to many of the problems. What is the heat interaction? What is the work interaction? What is the change in pressure? How much work is done? So that is how the questions are being framed in any thermodynamic problems. So this thermodynamic system can be broadly divided into three categories. The boundary, which this whatever I had given, can change its shape. Okay. Now, this broad, I would like to divide this, classify the system I would like to classify the system into three categories. Closed system, open system, and isolated system. Closed system, open system, and isolated system. Generally, these are how the questions are asked. Classify the systems and explain about them. Now, I will take one after another. First, I will take the closed system. With the figures, I would like to explain. Best example for the closed system is gases in a piston cylinder arrangement. What is a closed system? In the closed system, here no mass transfer, no mass exchange, no mass transfer between system and surroundings. This is a system, this is a surrounding. Supposing if you take this as a system, this as a surrounding, this is a boundary. If you take this as the boundary, this dotted line, you can take it as the system boundary. Boundary will separate the system from the surroundings. This is the boundary. Okay. Now here no mass transfer between system and surroundings. Only energy transfer. Only energy transfer. Energy transfer means either you may supply the heat or reject the heat, or work may be done by the system or on the system. Anyway, only energy transfer. Either Q or W or both. Only Q may be there, only W may be there, both may be there. So only energy transfer possible. Is the mass, can the mass enter there? No. Can the mass leave from the system? No, because piston is there, right? No mass can enter, no mass can leave. But heat may enter, heat may leave. Heat can happen anyway. Heat may enter or heat may leave also. Work can be done by the system or on the system. Anyway, gas may be compressed, gas may reject the heat, gas may expand, all kinds of work interaction and heat interaction possible, but no mass interaction. Okay. This is what is called as a closed system. Gases in a piston cylinder arrangement. Best example is examples I am writing. Whenever you see a gas in a piston cylinder arrangement, immediately we should name it as a closed system. Gas in a piston cylinder arrangement as shown in the figure. Number 2. Any other example you may think of? A football. Football, supposing you have kept a football in the midnight, in the evening you have kept in the ground. I left it there. In the morning temperature will go down. Heat transfer may be that by the midnight temperature will come down, right? There may be heat transfer from the air inside the football to the outside, but mass cannot change, mass cannot escape, right? A tube light in a room, it is a closed system. Nothing is entering, but energy interaction is there. If you just touch the tube light, you will feel hot, right? there is heat transfer from inside to the outside. If you touch the tube light, it is hot. So, heat is being rejected. And there is a work interaction also, electrical work being done. If you switch on the light, there is work, electrical current will go, it may do the electrical work. So, work interaction is there, heat interaction is there, but no mass transfer. In our house, there is a LPG cylinder is there, gas cylinder. We are not cooking anything, it is a closed system. A cooker, pressure cooker, your weight is kept there, weight you have kept on the pressure cooker, the heat is being supplied, inside the rice is boiling, whistle is also there, then it is a closed system until the whistle rises, it is a closed system. Football or rather tube light, these are all the examples for a closed system. But most of the engineering thermodynamic systems are open, they are not closed. Most of them. I will tell you what is the open system. Gases in a piston cylinder is the best example for the closed system where no mass can enter. Mass is constant, I can say mass is constant. Inside no mass is entering, no mass is leaving. Open system. Both mass transfer and energy transfer can occur between the system and surroundings. Mass can leave, mass may exit. This mass may enter, mass in, mass may be simultaneously leaving. This is a system, and then you can supply the heat, you may get some work. Okay. So, this is called as the open system. Mass may enter, mass may leave. And examples. Most of the examples, practical systems are nozzle, mass may enter, mass may leave. Of course, here Q is 0, in the nozzle Q is 0, W is also 0, but mass in, no? M dot mass in, mass out, nozzle. Turbine, turbine is an example for the open system. Okay. We can take, here comes the concept of control volume. When you talk about the open system, you have to talk about the word called control volume. Okay. What is, I will tell you what is a control volume now. Here the mass may enter, mass may leave. There may be heat losses also may be there. This is a turbine, it is an open system. Third example, most of the open systems, most of the engineering systems are open. Compressor. What is the purpose of the turbine? To give the work, right? To give out the work. Compressor is that which takes the work. this is the compressor, where low pressure fluid, mass in low pressure fluid. What is the purpose of the compressor? To increase the pressure. It is the high pressure fluid. C for compressor, work in here. Now you are giving the work input. Compressor, fan, blower, all belong to the same category. Okay. It is an open system example. So now when you talk about this control volume, what is this control volume? So any fixed region, say for example, this is a control volume. A space around, if you fix the space, this can be taken as the control volume. Control volume is a fixed volume around that open system into which mass may enter, mass may leave, and energy may enter, energy may leave. The boundary of the control volume is called as the control surface. Control volume as referred to the open system. Generally in case of the open system only we talk about the control volume. As referred to the open system, is a fixed volume in space is a fixed volume or region is a fixed volume or region around the open system so see this is the control volume. This is the control volume, right? When you take a control volume, you can take the boundary of the control volume anywhere. The boundary of the control volume only is called as the control surface. It is a fixed volume or region around the into which mass and energy means Q or W may enter or exit. May enter, mass and energy may enter or leave. The boundary of the control volume is called control surface. The boundary of the control volume is called control surface. Generally, when you talk about the control volume, that is pertaining to the open system only. You are speaking about control volume means you are indirectly referring to the open system. You take some region around that open system, and that region within that region, whatever you call it as it is called as a control within the system, right? Supposing if you take this as a compressor, no, this is my this white line, this white color line is the boundary of the control volume. Everything inside that that dotted white line can be thought of as a control volume, and the boundary of the control volume is called as the control surface. Through control surface, mass may enter. Through control surface, mass may leave. Through control surface, work may enter, and through control surface, work may leave. Okay. So control volume is majorly is connected or pertaining to the control volume is the other name of the open system, you can think. But thing is that fixed region around that control volume, you call it as a control volume, and the boundary of the control volume is called as a control surface. This control volume concept you will again see in the fluid mechanics also. In the fluid mechanics also you will see this word control volume. Okay. So think it like this. Control volume means another reference to the open system, where mass may enter, mass may leave, energy may enter, energy may leave. Energy means either heat or work or both. Okay. Now I had given just 3 examples. I can give some more examples also. Diffuser, throttle valve, pump, fan or blower, all are open systems. Mass can enter, mass can leave, energy can enter, energy can leave. So majority of the thermodynamic systems come under open only. Very few are closed. Now the third system is isolated system. In the closed system, only only energy transfer, no mass transfer. In the open system, both mass and energy transfer is possible. In the isolated system, neither mass transfer nor energy transfer. Neither mass transfer nor energy transfer possible between system and surroundings. Between system and surroundings, what is that separating thing? System boundary. Okay. No mass can enter, no mass can leave. Example, thermos flask. Once you pour a hot coffee and close that, that's all. Because it is insulated. Thermos flask is thoroughly insulated. Adiabatic wall it has. Adiabatic wall means which does not permit any heat transfer. No heat can enter, no heat. That is why it is whatever the hot coffee you are pouring, it remains hot. But of course, for a small amount of time. There must no work, no chance for any expansion or compression. Yeah. Where is the change for, where is the chance for expansion or compression? So no work transfer, no heat transfer. So it is a isolated system, no mass transfer. Okay. Number 2, this is more important, thermodynamic universe. The class, there was a small technical snag, that is why it was interrupted. I was giving the examples for the isolated system. Isolated system is that system wherein there is no mass transfer, there is no energy transfer between the system and the surroundings. I could give you two examples for the isolated thermodynamic system. Number one was thermos flask. Number two, the second example for isolated system is thermodynamic universe. Thermodynamic universe. When I say universe, thermodynamic universe, it is the combined thing of system plus surroundings. See, if this is system, everything external to the system is surrounding, right? System and surroundings are separated by the system boundary. If you totally combine into one, that is called as the thermodynamic universe. Thermodynamic universe is the system plus surroundings put together is called as the thermodynamic universe. When I talk about the universe, thermodynamic universe, I recall the most famous laws, the most famous statements of the Clausius regarding the first law and second law of thermodynamics. Clausius said the total energy of the thermodynamic universe is constant, but the total entropy of the thermodynamic universe keeps on increasing. I repeat, the first law of thermodynamics, in the words of Clausius, the famous scientist of thermodynamics, the first law of thermodynamics could he stated as, so in terms of thermodynamic universe, change in total energy of the thermodynamic universe is zero. That is, the total energy of thermodynamic universe is constant. That is the first law of thermodynamics, which is also called as the law of conservation of energy. The same Clausius, for the second law of thermodynamics, he stated that for the second law of thermodynamics, the total entropy of the thermodynamic universe is greater than or equal to 0. The total entropy of the thermodynamic universe keeps increasing. The entropy of the thermodynamic universe tends to be a maximum. That is called as the second law of thermodynamics. The total entropy of thermodynamic universe tends to be a maximum. Total energy of the universe is constant. The entropy of the thermodynamic universe will never, I can say other way also. Second law of thermodynamics can also be stated like this. The total entropy of the thermodynamic universe will never decrease. Either it remains constant or it will increase. When it will remain constant, when it will increase, that you will come to see later. Actually, you will come to see in the due course of time. The total entropy of the thermodynamic universe remains constant if the process undergone by the system is reversible. If the process is reversible, yes, the entropy of the universe may remain constant. If the process is irreversible, the entropy of the thermodynamic universe increases. It will never decrease. If the entropy of the thermodynamic universe decreases, means the second law of thermodynamics is violated, I can say. So, that will become the PMM2, perpetual motion machine of second kind. Fine. These are the important classification of the thermodynamic systems. Now, we know closed, open and isolated. Okay, having defined the thermodynamic system, now I would like to characterize the system. I would like to describe the system. How do you describe the system? By defining the state, by mentioning any thermodynamic properties. See, one person is there. Now you want to describe that person. You will attribute some properties, his personality, his mentality. So no, you will attribute some characters to that person and you will describe the person is so and so tall or fair or some characters you will assign to him. Similarly, when you want to describe the thermodynamic system, we will make use of the tools we will make use of the tools which are called as the thermodynamic properties. So here comes the concept of thermodynamic properties. Now, having defined the thermodynamic system, now I am defining what is a thermodynamic property. Any measurable or observable characteristic of a thermodynamic system which is used to describe describe its condition or configuration, of system is called thermodynamic property. Any measurable or observable characteristic of a thermodynamic system, what for it is used? To describe the condition or configuration of a system, or rather the state of a system, that means properties are the tools, thermodynamic tools meant for defining the state of the system. Thus, thermodynamic properties are the tools to define the thermodynamic state of system. Okay, what are the tools actually? How many tools are there totally and what are they? I am listing out examples of the properties: pressure, volume, temperature. These are the main frontline thermodynamic properties. Internal energy, enthalpy, entropy. There mainly 6 are there: pressure, volume, temperature, internal energy, enthalpy and entropy. And of course, 2 derived properties: Helmholtz function and Gibbs function. That's all. These are all the properties. Totally 8 are there: pressure, volume, temperature, internal energy, enthalpy, entropy, Helmholtz function and Gibbs function. This is Helmholtz function, U minus Ts. Of course, they are not that conventional. We will discuss them usually in the availability concept and forgetting about that Helmholtz function and Gibbs function. Remaining mainly there are 6 properties are there: PVT, UHS. Standard units, I am writing the units also. So always try to write them in kilopascal, volume in meter cube, temperature in Kelvin, total internal energy in kilojoules, enthalpy also in kilojoules, entropy is in kilojoule per Kelvin. Yes, totally 6 are there mainly. Okay. Any thermodynamic relations, any thermodynamic problem analysis is done in terms of these 6 properties. Okay. Now, I will having defined the properties. So, you understood now properties are the tools, they are the tools which are required to define the condition or configuration or rather the state of a system. The state of a thermodynamic system is defined with the help of these tools. Then the question comes, do you have to mention all the 6 properties to define the state? To define the state of a system, to define the condition of a thermodynamic system, should we have to give all the 6? No. How many properties are required usually? Usually how many properties are required to define the thermodynamic state. For a simple compressible substance, I repeat, for a simple compressible substance like air in a piston cylinder arrangement, for a simple compressible substance, homogeneous substance, usually we require two properties. Any two properties will be sufficient to define completely the state of the system. Actually, how many properties are required to define the state of a system? There is one rule is there. Gibbs phase rule. They call it as Gibbs phase rule. Degrees of freedom and number of chemical constituents, number of phases, based on which there is one rule is there. But putting aside that rule, for a simple compressible substance like air, you require two properties, any two properties, pressure volume or volume temperature or enthalpy internal, like any two properties will be sufficient. Usually we will be defining pressure volume or temperature entropy usually. Okay. Now, I'm writing that rule there. Usually for a simple compressible substance, like air, any doubts we are having, there is one link here being suggested. You may please post the doubts there. Then I will personally clarify your doubts in that link, through that link. We require any two independent thermodynamic properties to completely specify the thermodynamic state of system. Okay. Now, having defined the properties, now I will give the how to classify the properties. Now I am classifying the classification of thermodynamic properties, intensive and extensive. Intensive properties and extensive properties. Intensive properties and extensive. These intensive properties, the properties which are independent of the mass of the system are called as intensive. The properties which are independent of the mass of system are intensive. Example, pressure, temperature. Then how do you understand practically? Say for example, there is one room. Say for example, this room is there. This room has got a pressure of 1 bar, temperature of 25 degrees Celsius. Maybe mass of the air is set, for example, 10 kg, volume is 10 meter cube. This room has got a pressure of 1 bar, temperature of 25 degrees Celsius, volume of around 10 meter cube, mass of the air in this room is, say for example, 10 kg. Now what I have done, I have just constructed a wall at the center of the room. I have constructed a wall. So that wall will exactly divide the room into two equal halves. Then that side of the room has got 5 kg mass, this side of the room has got 5 kg mass. Okay. That side of the room has got 5 meter cube volume, this side of the room has got 5 meter cube volume. But does it mean that that side of the room will have 0.5 bar and 0.5 bar, or that pressures remain same? It remains the same. After construction of the wall exactly at the middle of the room, that pressure will still be 1 bar, here the pressure will be still be 1 bar. Temperature that side is 25 degrees Celsius, same as before construction of the wall. What is the temperature? Same temperature will prevail also, 25 degrees Celsius and 25 degrees Celsius. It will not become 12.5, 12.5. But the wall, you see the volume, after constructing the wall, the volume that side is 5 meter cube, this side is 5 meter cube, mass is 5 kg and mass is 5 kg. That means volume is dependent on the mass of the system, but not the pressure and temperature. So what is extensive properties? The properties which are dependent on the mass of the system. Which are dependent on the or extensive. Example, volume, in total internal energy, total enthalpy, total entropy. All the total properties are usually represented with capital letters. This is a total volume. This is the total internal energy in kilojoules. This is in meter cube. This is total enthalpy. This is the total entropy. So, these in fact these are all the properties we have classified. But when I say intensive, any specific property, please note that any specific property which is defined per unit mass. What now actually we are going to define is what is a specific property, specific volume, specific internal energy, specific enthalpy, specific entropy. These are all the properties defined per unit mass. Interestingly, all these specific properties are intensive properties. For example, specific volume is there. Specific volume, total volume by mass, meter cube per kg. Specific internal energy, whatever the property which is defined per unit mass, it is a specific property. Specific internal energy, it will be U by M, that is kilojoule per kg, like that. Look, so it is generally denoted with a small letter. It is generally denoted with small letter. So, similarly, small h, specific enthalpy, total enthalpy by mass. So, whenever I usually I denote specific properties with small letter. Small u is referring to the specific internal energy, small v referring to the specific volume. Or similarly, small s, that is total entropy by mass, kilojoule per kg Kelvin. Okay. So, all these specific properties interestingly will be intensive. All the specific properties by default are intensive. I can say the rule also. The ratio between any two extensive properties is intensive. The ratio between any two intensive properties, the ratio between any two extensive properties is intensive. If you look at this, total volume is extensive, mass is extensive, the ratio is intensive. So, earlier I have defined that, say this room has got 10 kg mass, this room has got 10 meter cube volume. But then what is the specific volume? 10 by 10, 1 meter cube per kg. But even after construction of the wall, now the wall is constructed. That side 5 meter cube volume, this side 5 meter cube. That side 5 kg mass, this side 5 kg mass. Then what is the specific volume if we calculate there? 5 by 5, again it is 1. Earlier, before construction of the wall, 10 by 10, that is also again 1. That means any specific property which is defined per unit mass automatically becomes intensive. Okay, that point please remember. Any specific property which is defined per unit mass is intensive. Thus, small v, small u, small h, small s, all are intensive. All are intensive properties. Okay. Right. Now, having defined the properties, now I will define the thermodynamic state. Thermodynamic state. What is thermodynamic state? We have defined the thermodynamic system. I want to describe the thermodynamic condition of that system by using the state. So for example, this room is there. At what thermodynamic state is there here? You have to mention its pressure or a temperature, pressure or a specific volume. Usually any two properties will be sufficient to define the thermodynamic state. So thermodynamic state is the condition or configuration of the system which is defined by any two independent properties, and thus that state could be plotted on a thermodynamic plane. Okay. Thermodynamic state means its condition or configuration which is described by any two independent thermodynamic properties. The condition or configuration of a thermodynamic system which is defined by giving any two independent thermodynamic properties, and thus the state is called state. The condition or configuration which is defined by giving any two independent thermodynamic properties is called thermodynamic state, and this state is given as a point on any thermodynamic plane, or thermodynamic diagram, maybe PV diagram, or usually we have two planes, PV and TS. On any plane, thermodynamic plane like this, that thermodynamic state is indicated as a point. Okay, this is a point. This is a thermodynamic state. And very importantly, I want to tell here that at a given thermodynamic state, there is only one unique value for any thermodynamic property. Here, very importantly, I want to tell that a thermodynamic state is defined. At that state, we have only one pressure. You don't see two pressures. At a given thermodynamic state, we have only one pressure, one temperature, one internal energy, one entropy. We don't see two pressures or two internal energies like. So, Any thermodynamic property, since it has a unique value at a given thermodynamic state, they are called as the point functions. When the state changes, supposing when the state changes, the property value may change. So, they dependent on any thermodynamic property value is dependent only on the state and not on how that state is reached. The past history of the system does not matter. At a given thermodynamic state, you have a unique value for any property, one pressure, one volume, one temperature, one internal energy, one enthalpy, one entropy. So, all these properties are called as the point functions, because when the point changes, that value, the property values may change. So, I want to tell that thermodynamic properties or point functions are exact differentials. You have only one pressure, we have only one specific volume, like that. Okay. So, their pressure and specific volume are point functions, because they are the properties. Any property is a point function. And usually I would like to tell you that usually any thermodynamic plane is usually drawn between two intensive properties. You observe any thermodynamic plane, usually it is drawn between two intensive properties, PV or TS, small letter I am putting. That's what is this small letter I am putting? Meter cube per kg, specific property. Specific property is used as a small letter there. So, I would like to tell that at any given thermodynamic state, there is only one unique value for any thermodynamic property. Thus, all thermodynamic properties are point functions, or point functions, or one more thing also, or exact differentials. Please remember them, these words, or exact differentials. That is dp, dt, du, dh, dv, ds, S is for a specific entropy, all are exact, all are exact differentials. All are exact differentials. And then we may say, what is inexact differential then? Inexact differentials, they depend on the path followed. And these properties are these properties are having a unique value at a given thermodynamic state. When the state of the system changes, the property values may change, right? So, point to point, the values may change, because at a different thermodynamic state you may have a different pressure, you may have a different volume. These are all exact differentials. Okay. Now, and actually the only 6 are there. There is actually one more property is also there, that is a product of pressure and volume, which is called as a flow work. Incidentally, one note also I am writing. Incidentally, the product PV is also a thermodynamic property. What is the name of this thermodynamic property? Called flow energy or flow work. Flow energy or flow work. PV is a also a thermodynamic property. Flow energy or flow work, it is a thermodynamic property, and when you add your internal energy and flow energy, we get the thermodynamic property called enthalpy. Okay, now we have defined a property, we have classified the properties, we know what is exact differentials. And what is an exact differential, I would like to tell you. Supposing if a system is undergoing a thermodynamic process, this is initial state 1, final state 2. System is undergoing two different paths. Supposing from here to here, one path it is following. From here to here, it is a different path it is following. Okay. Exact differential means the change of pressure between 1 and 2 is the same for path A and path B. For path A and path B, the change of the property pressure is same, that is delta P between 1 to 2, that is P1 minus P2 we can say, is same for both the thermodynamic processes, is same for both the thermodynamic paths A and B. That is the meaning of exact differential. That is true not only for the pressure. That is true not only for the pressure. For all the thermodynamic properties, this rule is applicable. Similarly, delta H is same between 1 and 2 for the path A and B. Delta H between 1 and 2 is same for path A and same for path B. Delta S, delta change in entropy between 1 and 2 is same for path A and path B, thermodynamic 2. That is the meaning of exact differential. Okay. Now, you understood what is an exact differential means. Remember that all the properties are point functions are also known as exact differentials. Now, I will define thermodynamic process. Whenever a thermodynamic system undergoes a change of state, whenever a thermodynamic system undergoes a change of state, it is said to have undergone a thermodynamic process. Whenever a system undergoes a change of state, from one state to another state, the system has undergone this is the initial state, this is the final state. This can be, this is a thermodynamic process, and this process while undergoing may have so many intermediate states, right? These are all the intermediate states. The series of thermodynamic states, the series of thermodynamic states undergone by this system during the process, the series of thermodynamic states, this is one state, next state, next state, like this. The series of thermodynamic states undergone by the system during the process, when joined, we get the thermodynamic path. The thermodynamic path is obtained by joining the series of states, by joining the series of states undergone by the system during the process. When we join all those states, we get the thermodynamic path. Okay. Thermodynamic path is obtained by joining the series of states by joining the series of states undergone by the system during the process. And when this is 1 to 2, this is the thermodynamic path. This is the thermodynamic path. Okay. Here comes the another differential called inexact differential. I said earlier all the thermodynamic properties or point functions are inexact differentials. That means the change of a property between two given end states is independent of the path followed. That is one important thing. That is called as a exact differential. I would like to state that point here also. Note as the change of a thermodynamic property any thermodynamic property, because totally I have 6 properties defined P, V, T, U, H, S. The change of a thermodynamic property between two given end states is independent of the path followed by system. See, look at this. For this path and for this path, the change of the any property, though I have written here for the pressure, it is true for the internal energy, it is true for the enthalpy, etc. Okay. Now, we have got a thermodynamic path. What is a thermodynamic path? The series of states undergone by the system during the process when we joined, because from between the initial state and final state, system might have gone through say a series of states. When we join all those states, we get the thermodynamic path. Okay. Now, here comes that a path function or inexact differential. Heat and work are path functions, also called as inexact differential. Heat and work are path functions or inexact differentials. That is delta Q and delta W are inexact. Usually, if you write the D total, no D, if you write the DU, DH, they are the exact. For indicating inexact, we write delta Q and delta W are inexact. Heat and work are path functions. They depend on the path followed. We will see later. So why they are path functions, we will see. Now we have defined a system, we defined the property, we defined the state, we defined the process. So process means whenever a system undergoes a change of state, it is said to have undergone or it is said to have executed a thermodynamic process. Okay. Then now I will define a cyclic process. What do you mean by a cyclic process? Later in future in thermal engineering we will see so many cycles: Carnot cycle, Otto cycle, diesel cycle, Breton cycle, Rankine cycle, etc., etc. So many cycles, Stirling cycle, so many number of thermodynamic cycles we will see. Some are clockwise, some are anti-clockwise. See, most prominent thermodynamic planes are PV and TS. There is one more plane is there called also, they are complementary to each other. See, what is the meaning of a thermodynamic cycle? After undergoing a number of thermodynamic processes, similarly the same cycle may appear in a different direction like this. If you plot it, it may appear like this. Shape may change. But one thing is certain, if this is a clockwise here, this will also be clockwise here. If this is an anti-clockwise, that also an anti-clockwise. What do you mean by thermodynamic cycle? A system beginning at one thermodynamic state, and after undergoing a number of thermodynamic processes, maybe 2, 3, 4, 5, it's any number may be there, but here I am showing only for simplicity, I am showing the 2 processes constituting this cycle. But sometimes there may be 4, 5, most of our thermodynamic cycles have 4, including Carnot cycle. One cycle has 5, that is a dual cycle, except that rest of all there is got 4 processes. Only one cycle has 3, that is called Lenard cycle. Lenard cycle has 3, dual cycle has 5, rest of all cycles have got 4. Most of the cycles have 4 processes. So, beginning at one thermodynamic state, starting at one thermodynamic state, and after undergoing a number of thermodynamic processes, if the system comes back to its initial state, after undergoing a number of thermodynamic processes, if the system comes back to its initial thermodynamic state where it has begun its journey, it is called as a thermodynamic cycle. Beginning at one thermodynamic state, and after undergoing a number of thermodynamic processes, maybe 3, 4 or 5, and after undergoing a number of thermodynamic processes, if the system comes back to its initial state, it is said to have undergone a thermodynamic cycle. It is said to have undergone a thermodynamic cycle. See, now incidentally, you are beginning the journey here, and after undergoing a number of processes, it is coming back to the initial state. I already said earlier, at a given thermodynamic state, there is only one unique value for any property, given thermodynamic property. You have only one pressure at a given state, you have only one entropy, you have only one temperature. One state means one property value. That property could be anything, maybe pressure, volume or temperature. Because you have arrived at the same state, that means what is the net change in any thermodynamic property? It will be 0. Because you have arrived at the same state, the net change in the property around the cycle will be 0. Because any given property has a given unique value at a given thermodynamic state. You have begun here journey, certain pressure is there. After undergoing, you have come to the same state. That means what is the net change in the pressure around the cycle? It should be 0, because you have come to the same state where you have begun the journey. Since any thermodynamic property is a point function cyclic integral of this this round indicates cycle, maybe clockwise or anti-clockwise. Any thermodynamic property should be equal to 0. That is, this round indicates cycle. Or we could write all of them is equal to 0, because P, U, V all are properties, H, entropy all are properties. The net change in the thermodynamic property around the cycle should be 0. Whether it is a clockwise or anti-clockwise or a reversible or irreversible does not matter. For any thermodynamic cycle, let it be, I am very clearly writing here, this is for any cycle. When I say any cycle, maybe a clockwise cycle or anti-clockwise cycle, reversible cycle or irreversible cycle, for any cycle this rule is valid. Because at a given thermodynamic state you have a unique value for any thermodynamic property. Generally, when the cycle is a clockwise cycle, generally any clockwise thermodynamic cycle is a work producing cycle. Is a work producing cycle or heat engine cycle. Heat engine is meant for that. In thermodynamics, heat engine means work, it produces work. Where IC engine is a heat engine. Steam power plant is a heat engine. Gas turbine power plant is a heat engine, because all these heat engines will give you net work output. They produce shaft power. They produce mechanical shaft work. Any clockwise cycle is a work producing cycle or a heat engine cycle. Example, Otto cycle, Rankine cycle, etc. In fact, including the Carnot cycle, I can say. Any anti-clockwise cycle thermodynamic cycle is a work absorbing, they require work. Is a work absorbing cycle or refrigeration or heat pump. There are two things again. Refrigeration or a heat pump cycle. Any anti-clockwise cycle. For example, I am giving vapor compression, refrigeration cycle, reversed Carnot cycle. Vapor compression, refrigeration cycle. Okay. Now we have defined the thermodynamic cycle also. Okay, we have now defined the system, we have defined the property, we defined the state. Now I define what is a thermodynamic equilibrium. Thermodynamic equilibrium. It comprises three different kinds of thermodynamic equilibrium consists of three different kinds of equilibriums. Number one, mechanical equilibrium. Number two, thermal equilibrium, and number three, chemical equilibrium. Only when all the three equilibrium conditions are satisfied, then only the system is supposed to be in thermodynamic equilibrium. Actually, it comprises of mechanical equilibrium, thermal equilibrium, and chemical equilibrium. Mechanical equilibrium means what? See, for example, a room is there. A room or a container is there. So, at one location we have one pressure, at another location you have a different pressure. Say for example, within that room, at one corner you have one pressure, at a different corner you have a different pressure. What will happen? Immediately the flow begins. The flow begins. The flow happens, the flow of the fluid. How long it will happen? How long the pressures at both the locations become equal? How long the flow would happen? As long as the pressures at both the locations will just become equal, that will the flow happens. Once the pressures at both the corners become equal, there is no further change of the state, or rather the system will, entire system will be at having only one pressure. Supposing if I want to mention the pressure of that system, at one corner you have one pressure, at different corner you have a different pressure. Which pressure you will mention? You will wait until the flow happens and the things get settled down. That means at both the locations you will have the same pressure. Then that pressure can be used as a thermodynamic tool to define the state of the system. That means a mechanical equilibrium is said to be established only if there are no pressure gradients. There are no pressure gradients everywhere within the system. The same pressure must prevail. That means at every location, at every corner, we should have the same pressure value. That means no pressure gradients. Between any two locations. Within system. No pressure gradients between any two locations within. That means delta P is 0. Mechanical equilibrium means the difference of pressure between any two locations is 0. What is the thermal equilibrium? Suppose that suppose that there is a thermodynamic system at two different locations I have selected. Here there is a one temperature, here there is a different temperature. Then immediately heat transfer begins, because heat transfer is a phenomenon which occurs whenever there is a temperature difference. How long that heat transfer could happen? That heat transfer may happen by conduction, convection, or whatever the way, but definitely if there is a temperature difference between any two locations within the system, heat transfer starts as long as there is a temperature difference. And how long it will happen? Once the temperatures become equal. That means once the temperature becomes equal, there is no any further heat transfer. That means no temperature gradients. That is called as the thermal equilibrium. Delta T should be equal to the 0. That means all the locations within the system must have the same temperature. No temperature gradients. No temperature gradients between any two locations. Then that system is supposed to be in thermal equilibrium. All the I mean, like all the points within the room, suppose that if they are having the same temperature, yes, that is a bit thermal equilibrium. Thermal equilibrium means having the same temperature. Because here in this context I will define one important law, zeroth law of thermodynamics. Chemical equilibrium means no chemical reaction or no change in chemical species. No change in chemical species within the system. So even if there is a reaction, the rate of forward reaction should be equal to the rate of backward reaction. No change in chemical species. So that is called as the chemical equilibrium. And a thermodynamic system is supposed to be in thermodynamic equilibrium only when all the three equilibriums get satisfied. Only when all the above three equilibrium conditions are satisfied, only when all the above three equilibrium conditions are satisfied, then only system is said to be in thermodynamic equilibrium. The system is said to be in thermodynamic. No temperature gradient, no pressure gradient, no change in the chemical species or chemical composition. Whatever the chemical composition is there within the system, that must not change with respect to the time. So then only that system is supposed to be in thermodynamic equilibrium. See, we can define clearly the state of the system only when the system is in thermodynamic equilibrium. We can completely define the state of the system only if it is in thermodynamic equilibrium. Supposing in a thermodynamic system there are two pressures, which pressure you mention? So you have to wait. How long you have to wait? Till both the locations have got the same pressure, because whenever there is a gradient, whenever there is a potential difference, like temperature difference is a potential difference, thermal potential, heat transfer happens. How long it will happen? When both the locations are arriving at the same temperature. As that temperature could be selected as a property of the system at that particular state after arriving the thermal equilibrium. That means what I am going to say is, thermodynamic state can be plotted or indicated only when the system is in thermodynamic equilibrium. Otherwise, we cannot plot the state of the system. Usually, as I mentioned, for a simple compressible substance, usually any two properties will be sufficient to describe the state of the system. Pressure volume or temperature entropy. Usually we consider in our thermodynamics two planes we talk, PV and TS. There are two more are also there, HS Molier chart and pH chart is also there. pH is used in refrigeration. Molier chart is used for steam, particularly for the steam. Molier chart, that is enthalpy versus entropy chart, will be used. But most commonly we use, very commonly in all the thermodynamic problems, PV is the main. Second thing is the TS, temperature entropy. Right. Now I will define, having understood the thermodynamic equilibrium, now I will define the quasi-static process, very important process. Quasi-static process. See, this is one thermodynamic system I have considered, a closed system, a piston cylinder arrangement, a gas is there inside, maybe air. Over that there is one weight I have kept, considerable weight I have kept on the piston. Initially the system is in thermodynamic equilibrium. Therefore, once the system is in thermodynamic equilibrium, we can plot the initial state. Now what I have done, this weight I have removed, this weight I have just removed from that piston. Considerable weight, the weight I have removed. The moment you lift the weight, immediately the piston shoots up. The air expands instantaneously upwards, and finally after a certain time, after a certain stage, instantaneously it jumps up and finally comes to halt. Once it comes to halt, things will settle down. I have given sufficient time. Initially the piston is under weight. Once you remove the weight, immediately piston will shoot up and finally it settle down at some location after expansion, and I have given sufficient time for the things to get settled down, and after arriving the final location, and again I have noted the final state, the pressure, and two properties I could measurable properties, observable properties. What is the use of measuring a property? We can define the state, at what condition the thermodynamic system is. After a piston is expanding, after stopping, and again taken the two properties, I defined the state of the system. We know the initial state, we know the final state, but can you draw the path? Can you join the initial and final? Are you aware of the intermediate state points? You can't draw the path because you are not aware of the intermediate state points. Why? Because the process has occurred so quickly that there is no way that you can measure the intermediate states and plot it on a thermodynamic plane. You can get the path only when you are aware of the intermediate states. There is no such thing could happen here, because the piston has suddenly, as a knee-jerk like thing, suddenly it jumped up, and you are not aware of the intermediate states. You can't get the path. You can't join the process states, intermediate states. Now what I do is, in the another kind of experimentation, same weight. Now I have taken a 1 million slices, same weight, I have taken 1 million slices. Suppose that so many number of slices are given, so many. Imagine that so many slices, and each layer initially I have plotted it. Initial state I got it. Initial state, before removing the any slide, 1 million layers, imagine that weight. One layer I am removing, each layer I am removing. So after removing the first layer, first state, like that. So each layer after removing, I got the 1 million state points, all of them is joined, and I got the thermodynamic path. Got it? So that after each layer I am just removing one after another. Same gas now is expanding. Now because you are removing one layer one after another, the system is expanding, but the expansion is happening at such a slow pace that each and every state during that expansion is almost in thermodynamic equilibrium. Okay. It is no doubt the system is deviating, changing its state from one to one, but the change of state happening at such a slow pace that the system is almost in thermodynamic equilibrium. The deviation of the system from thermodynamic equilibrium is infinitesimally small. No doubt it is deviating from thermodynamic equilibrium. As the system moves from one state to the another state, it is deviating from the thermodynamic equilibrium, but the deviation is very small, infinitesimally small. That process could be called as a quasi-static. Quasi means semi. Static means rest, at rest. Generally static means you say at rest. You are observing that process is happening at such a slow pace that the system is almost in static condition. That is what is called as a quasi-static, quasi-equilibrium process. The deviation is happening from thermodynamic equilibrium. As the system goes from one state to the another state, next state, it is deviating from thermodynamic equilibrium, but the deviation is very small. You can think that it is almost in thermodynamic equilibrium. So that kind of a process is called as a quasi-static. So here no path can be obtained, but there path is obtained. No path is obtained because you are not aware of the intermediate states. Here you are aware of the intermediate states. We got the thermodynamic path by joining all the states. So this kind of a process, this is the quasi-static process. So how much time it would have taken by the system to undergo the quasi-static process? Infinite time, because it is happening at very slow pace. So I am defining the quasi-static process. While undergoing a process, if the deviation of the system from thermodynamic equilibrium while undergoing a process, if the deviation of the system from thermodynamic equilibrium is infinitesimally small, at each and every state, then such a process is called quasi-static, which is also called quasi-equilibrium. Thermodynamically, some books will give it as a quasi-static or quasi-equilibrium process. It takes infinite time. It takes infinite time to complete a quasi-static process. Now I will having defined the quasi-static quasi-equilibrium process, now I will derive an equation, very important derivation here. How much work is done during that, assuming that the process is a quasi-static process and the system as a closed. To derive an equation for work done during a quasi-static process undergone by closed system. A closed system is undergoing a quasi-static process this is the initial state 1, this is the final state 2. A system is undergoing a closed system, a gas is undergoing a quasi-static process from the state 1 to the state 2. Now, I considered the system is closed and the process is quasi-static. Now, I considered a differentially small displacement of the piston. I have considered a differentially small displacement of the piston during which the pressure acting on the piston is P. Suppose that A is the area of the piston. Let A is equal to area of the piston and dx be the differential displacement of the piston. So, consider differential displacement of piston during expansion process is quasi-static. We are aware of the intermediate states. Consider differential displacement of the dx of the piston during expansion during which the pressure acting on the piston is P. Exerted by gas. P is the pressure exerted by gas during that differential displacement dx. process is undergone by the closed system is quasi-static, but I just considered a differentially small displacement dx of the piston during which the pressure acting by the gas on the piston is P. Then force exerted by gas on piston during differential displacement is equal to pressure into area. So many Newton. Pressure into area is a force, right? Hence, differential work done by gas, differential work done by gas during differential displacement F into dx, pressure into A into dx become pressure into dV is the where dV is equal to differential change in volume. Differential change in volume of the gas during that differential displacement. So, therefore, delta W is equal to PdV by gas during quasi-static, which is all quasi-static process, also known as, it is also many times it is known also known as internally reversible process. Internally reversible process. Quasi-static process is also known as internally reversible process. I would like to tell here. It is also known as internally reversible process. Other name of the quasi-static process is internally reversible. Now we get the total work done. If you want to get, it is integral delta W between the limits 1 to 2 integral PdV between the limits so many kilojoule, because I am using the small letter here, work done per unit mass I am expecting. Work W12. Now we have come across the very important point in thermodynamics. Work done by a closed system during a quasi-static process, but two conditions must be satisfied to use this formula. Two conditions must be satisfied. System must be closed and the process must be quasi-static, also known as reversible. Quasi-static, other name of that is or reversible. So, quasi-static or reversible work done by closed system during a quasi-static process is integral PdV. Incidentally, this integral PdV is the area of the PV curve on x-axis. This area is integral PdV, area on x-axis, area under curve. Actually, of course, y-axis area is different, that is integral VdP, that is the steady flow work done, that is also reversible, but that is for the open system. This is for the closed system. So, now mind that when you can write the integral PdV, work is equal to integral PdV under two conditions satisfied. Number one, system must be closed and the process must be quasi-static. Okay. Work done by closed system during quasi-static or reversible process. Quasi-static or reversible both mean the same. Quasi-static, quasi-equilibrium. Very important point. This is delta W is equal to PdV. Delta W is equal to integral PdV, area of the curve on x-axis. Just take a 5 minutes break. After the break, I will continue. Any doubts you are having? I will be clearing your doubts. And there is one community group, and we have a one mechanical engineering community group for all the subjects. For all the subjects we have, and any doubts you are having, you may post it there. We will be able to solve and Hello students, welcome back to the class. We have derived the equation before the break that integral PdV is the formula for the work done by a closed system during a quasi-static or reversible process. So, I have defined what a quasi-static process is. First of all, what do you mean by thermodynamics? What is the main difference between a conventional work what we have defined in the engineering mechanics and what is the difference between thermodynamic work? Thermodynamic work and applied mechanics work what we have defined earlier in engineering mechanics. What is the main difference? I would like to tell you. So, what do you really mean by a thermodynamic work? I would like to highlight here. I would like to define thermodynamic work. Now I am discussing about work transfer and heat transfer. What do you mean by thermodynamic work and what are the various modes of thermodynamic work are there? When do you say that a system is doing a thermodynamic work? That is what I would like to highlight here. See, look at this example. Suppose that there is one battery. It has got a positive terminal, negative terminal. There is a switch. One electric resistance is there. So, this is the boundary of the system. Say for example, this is the boundary of the system. This is the system boundary. Now, I have closed the switch. I have closed the switch and then immediately current will flow and resistance will get heated up. Then do you say that work is set to any thermodynamic work is done? A battery is there, there is a switch, I close the switch. Once I close the switch, the current will flow. When the current flows through the resistance will get heated up. Do you say any thermodynamic work done is the work is done there? No. Generally, you will think that it is no, but my answer is yes. Yes, there is a thermodynamic work done. How is it done? Thermodynamic work done? It is like this. If same system, same particular figure I would like to modify like this. Instead of resistance, I keep a small motor. Motor will have an output shaft. That output shaft of the motor is linked with one pulley, and to that pulley there is a one weight hanging. Okay. Once the switch is closed, this is the thermodynamic system boundary. This is the system boundary. This dotted line is a system boundary. Now, once I close the switch, now this shaft will rotate, this will weight will move up. Okay. Once this switch is closed, current will pass through the motor and motor shaft will rotate, and through the there is a pulley, small pulley is there, frictionless pulley, and weight will move up. There is a displacement of the weight. Now, do you say that any work is done in this figure? Yes. Now, there is a work done. Now, the same thing I could say here also. Here also work is done. In this configuration also, first figure also work is said to be done by the system. So, how do you define a thermodynamic work? A thermodynamic work is said to be done by a system if the sole effect external to the system can be reduced to the raising of a weight. A positive thermodynamic work is said to be done by a system if the sole effect external to the system can be reduced if the sole effect external to the system can be reduced to the raising of a weight. So, this is how we understood the thermodynamic work. A positive thermodynamic work is said to be done by a system if the sole effect external to the system, external means beyond boundary, can be reduced to the raising of a weight. In the second figure, you are telling that yes, thermodynamic work is done. Here also I said that here also thermodynamic work is said to be done by a system, because same thing is reduced to the first figure is reduced to the second figure. Okay. If the sole effect external to the system can be reduced to the raising of a weight. Now, I will just tell about what are the various modes of thermodynamic work. We have already defined PdV work, we have already indicated a PdV work. Various modes of thermodynamic work. Now, earlier I have defined PdV work. Of course, closed system and quasi-static process, that is reserved for that. Integral PdV minus integral VdP. Reversible work done by R on a steady flow open system. What is steady flow? I will tell you later. For the time being, remember the minus integral VdP is the example compressor, pump. Okay. Electrical work. Suppose that there is a one container, there is a resistance, some current is passed. Okay. Electrical work. What is the formula electrical work? I square R into time. T is the time, so many joules. Electrical work. Current is passing. This is the boundary. This is the boundary. When the current is passing, work done on the system or by the system? It is on the system. Actually, I would like to give the convention of sign convention also. Work is positive if work done by the system. If work done by the system, it is positive. Work is negative if work done on the system. So, for example, what is the example here? Work done by the system, expansion. So, expansion work. Example, I can say example, expansion of a gas. Gas expansion, it is the positive. Example here, work done negative, compression. Compression work is a. So, now for example, compression, if you take the compressor as a system, work is negative or positive? Negative, because unless otherwise we do the work on the compressor, it can't run. If you take the pump, negative work or a positive work? Negative work, because for the pump you have to supply the energy, you have to do the work on the pump to lift the water. For the pump, work is negative. For the compressor, work is negative. For the turbine, work is positive. I can say expansion work, I can give here. This is a positive work for the turbine. For the compression means compression, pump, all these are negative works. Okay. Electrical work. Here work done negative or positive? It is a negative. Why negative? you are supplying the current. Unless otherwise you supply the current, that resistance will not get heated up. This is a system boundary electrical mode of work. Paddle wheel work. Suppose that there is air, there is one paddle wheel running against the viscosity of air. This is again negative work. Negative work. Paddle wheel work is a negative work. This is because you are stirring the air. Negative work. The work quasi static, in fact expansion is positive work, compression is negative. These are all the various modes of works: electrical work, paddle wheel work, integral PdV. In fact, I am using the word reversible here. What is actually reversible and irreversible? That we should distinguish now. Earlier I have defined a thermodynamic process. Whenever a system undergoes a change of state, it is said to have undergone a thermodynamic process. Then I have defined a quasi-static process. While undergoing a process, if the deviation of the system from thermodynamic equilibrium is infinitesimally small, that is called as a quasi-static process, quasi-equilibrium or quasi-static process. Then what is this reversible and irreversible process? That is, this is a very great distinguishing phenomena in thermodynamics. In thermodynamics, this is a very crucial thing to understand, to distinguish between reversible and irreversible. What makes a process irreversible? Is the reversible process practically feasible? All these questions one should be able to answer. In the thermodynamics, the concept of reversibility is very, very important, because there is only one cycle which is completely reversible, that is Carnot cycle. All other cycles are irreversible only, actually, all other thermodynamic cycle. Then what is this meaning of this reversible and irreversible processes? I will discuss. Now I have put up various modes of the work transfer. And how about the heat transfer? Heat is the only mode of energy transfer which happens because of the temperature difference. All other modes of energy transfer are work only. All other forms of work, energy transfer are work. Heat is the only mode of energy transfer which happens because of the temperature difference. It is the only mode of energy transfer that occurs between system and surroundings because of temperature difference or thermal potential. It is also called as all other energy transfers come under work transfer only. Because the thermodynamics is after all subject of heat energy transfer and work energy transfer. Except this particular mode, heat energy, when can you expect a heat energy transfer between the system and the surroundings? Only when there is a temperature difference. If there is no temperature difference, there is no heat energy transfer. So all other forms like electrical work, PdV work, minus integral VdP of all are come under work transfer only. Okay. Paddle wheel work, electrical work, and also expansion of a wire. All these things. Supposing a wire is there, you are expanding that wire. You are expanding that wire by exerting a tensile force, that comes under again a work transfer. That is that force into displacement, that will give the what is the strain energy stored inside the member. as you have done in the strength of materials also, that is again comes under work transfer. Whatever the work you are doing, and that will get stored inside the that wire in the form of the strain energy. Okay, like you are stretching a spring is there, spring work. It is another mode of work of kx square. For example, if we just include that as a spring work, compared with k is the spring constant, x is the displacement, k is the spring constant. So everything else is a comes under work transfer only. I had given the sign convention for the work. Work is positive when work done, if work done by the system, if work done on the system, it is a negative. Fan, compressor, pump, all are negative works. Turbine is a positive work. Any expansion of the gas is a positive. Any compression of the gas is a negative. Then how about the sign convention? How about the sign convention? How about the sign convention for the heat energy? Q, that is the heat transfer, positive if supplied to the system. This is a sign convention. If supplied to the system, positive. If rejected from system, negative. See, Q and W, heat transfer and work transfer are path functions. Why they are path functions? Q and W are path functions. Or inexact differentials. Or boundary phenomenon. They occur at the boundary or boundary phenomenon. They cross work is said to be done by a system only when it crosses the system boundary. Heat is supplied to the system only heat is said to be supplied to the system only when it crosses the boundary. Whenever you talk about the work transfer and heat transfer, just check around the boundary. Because heat energy and work energy are the energies in transition between the system and surroundings via boundary. That is why they are called as the boundary phenomenon. Heat and work, Q is the heat, W is the work. Heat and work are energies in transition between the system and surroundings via system boundary. So that is why they are always called as the boundary phenomenon. Heat and work are never possessed by the system. If somebody says to you, does the system has heat? You will say, no, it is a wrong statement. System will never possess the heat. System will never possess the work. But system has pressure. System has volume. Thermodynamic system has temperature. It has a pressure. It has a volume. It has got internal energy. It has got enthalpy. But somebody says system has so and so heat. Yes, wrong. That is wrong. Because a system never possesses heat. Heat is a form of energy in exchange, in transition between the system and the surroundings via boundary. They are boundary phenomena. They are path functions. They are inexact differentials. Whereas the what system possesses, what system has, they are the properties. They are the point functions. They are exact differentials like pressure, volume, temperature. These are all the exact differentials. They are possessed by the system. they are in fact a system is there, system characters there. So in fact they are the properties of the system. To define the state of the system, these are used. But heat and work, they are never possessed by the system, because they are always being exchanged from the surroundings to the system or system to the surroundings. That is why they are a path function. Once the path changes, the heat transfer will change and work transfer will be changed. I will give the example here. Suppose that on a PV plane, there is a one thermodynamic process between the initial and final states. Between the same initial and final states, there is another process B. This is process A, path B. This is the initial state and this is the final state. Now, between these two states 1 and 2, there are two different paths. Heat transfer under work transfer under path A and work transfer under path B will be different. W1 to 2 along path A definitely will not be equal to the W1 to 2 along path B. Similarly, why so? What is the reason? What is the reason for this? Because the area under 1 to 2, what is the reason here? I am giving the reason also. Reason is area under 1 to 2 on x-axis is not equal to area under 1 to 2 on x-axis along A, along path A. Area under 1 to 2 on x-axis along path B. The areas are different, works are similarly Q 1 to 2 along A is not equal to Q 1 to 2 along path B. That is why hence heat and work are path functions. They depend on the path followed. They depend on the path followed. But one thing I would like to highlight, but delta P 1 to 2, that is P1 minus P2 is same along path A and path B. That is true for all the properties, need not be pressure. That means the change of a property between two given end states is independent of the path followed. That is very important point. Thus, the change of any thermodynamic property between two given end states is independent of the path followed. is independent of the path followed between those two states. Is independent of the path followed between those two states. Once the two states are fixed, end states are fixed, whatever may be the path you join between them, whatever may be the path, the change of any given thermodynamic property is same for all the paths. That property could be anything, maybe pressure, maybe temperature, maybe internal energy. That is true for all the properties. That is why all the properties are called as point functions. They depend only on the end states, not on the path. But whereas the heat and work, though end states are same, for this path heat transfer is different, for this path heat transfer is different, for this path heat transfer is different. Similarly, that is true for the work also. That is why work and heat are path functions. They depend on the path followed. They are the boundary phenomenon. I hope you understood the main difference between all the properties on one side and heat and work are on the other side. Okay. Now, we understood about the variations between heat and how the work could happen, work transfer could happen. And you know the sign convention, work is positive if done by the system, work is negative, work done on the system. Heat is positive when supplied to the system, heat is, supposing a tubelet is there, just example I am giving. A tubelet is there, a tubelet, I am just showing the example. A tubelet is running inside is lighting inside a room. A tube light, right? Now here, if you tell me sign convention, if you tell me a Q, W, is it 0? You have to tell me Q is 0 or a work is 0 or a positive or negative, you have to tell me. Definitely you can say that if you consider the tube light as the system, if you touch the tube light it will be hot. That means heat has been rejected from the system. That is Q is negative. Then how about the work? Only when you put the switch, tube light is on. That means current is going into the tube light and that is converted into the light energy. So work is done on the system or by the system? On the system. Unless you put on the switch, you cannot, your tube light will not be on. So W is negative. What kind of, Q is negative? Work is also negative. What kind of work this is? Electrical work. Because there are various modes of thermodynamic work are there. Okay. Supposing in the room there is a ceiling fan. In the room there is a ceiling fan, a fan there. A fan is rotating inside a room. Now, if you take this as a system, say control volume, this is air goes, air comes in, air goes out. Okay. Here W is negative, again electrical, or shaft work. And suppose if you take up to here only, up to take here the system, because shaft work done by motor, there is a motor is there in the ceiling, negative, paddle wheel work or shaft work. Motor is doing shaft work there, negative, work is done on the system. Q is 0 because within no time air can go almost 0, adiabatic. We can take it as an adiabatic. Q is 0. Okay, a car battery is there, a car battery, automobile car battery. Automobile car battery, work is done by, work is supplied, electrical work, no? Work is positive, electrical work is positive. Heat transfer almost nothing is there. An automobile car battery, no, it won't get in. Suppose the battery will not get heated up, but sometimes there may be a little bit heat loss, but work is positive there. For a car battery, work is positive because it is starting the car. For a automobile car battery, work is positive because it is able to start the car, because it is doing the work, it is supplying electrical work. It is doing an electrical work because it is supplying the electric current. And supposing like how to understand in a proper manner the sign convention. A automobile car battery, work is positive because it is supplying the electric current to the ignition, self ignition starting motor, that it is so it is a work is positive. How about the heat transfer means for a small amount of time Q can be taken as 0 because no heat transfer beyond that, it won't get heated up rather or cooled up. Right. Now, having understood these sign conventions of the heat and work transfer, now I will give the distinguish between reversible and irreversible processes. This is how we can define the reversible process. Suppose that a system has undergone a thermodynamic process. When can you call this process as a reversible? A thermodynamic process is said to be called as reversible when, after undergoing the process, if the system can be brought back to its initial state along the same path but in the reverse direction. A thermodynamic process is said to be reversible after undergoing a process if the system can be brought back to its initial state along the same path but in the reverse direction, without producing any changes either in the system or in the surroundings, then that process can be called as a reversible. That means you should not leave any evidence or proof that the process has ever occurred. A reversible process, when it happens, it does not leave any kind of proof or evidence that the process has ever occurred. That kind of a process is called as a reversible. It is purely an imaginary, hypothetical, theoretical process. All practical processes to some extent or greater extent, all are irreversible. All practical processes, all real processes, what we come across in our day-to-day life, all are irreversible. Now, first I'll write the definition of the reversible process. After undergoing a process, after undergoing a thermodynamic process, if the system can be brought back to its initial state, if the system can be brought back to its initial state along the same path but in the reverse direction, without producing any changes either in the system, without producing any changes either in the system or in the surroundings. Such a process is called reversible process. Without producing any changes either in the system or in the surroundings, such a process is called a reversible process. Reversible, in fact, it is example I am giving. Supposing there is a system, to this I have supplied Q say 100 kilojoules. System has done some, say it is 70 kilojoules work expansion. Now, this process can be called as a reversible if you should be able to give the exactly, you should be able to give the exactly the 70 kilojoules work you should give, exactly 100 kilojoules heat you have to take out. System must exactly come to its initial state, and surrounding, there should not be any change in the surroundings, there should not be any change in the system. Whatever the work you are getting, exactly you should be able to give 70 kilojoules, and exactly we should take out 100 kilojoules. How is it possible? It cannot be possible. Why? Because there is a mechanical friction here. Whenever there is a mechanical rubbing friction, some of the work, so to overcome that friction, some work will be spent. Whatever the work spent in overcoming the friction will get converted into heat. There is some heat generated. That means while taking out, when you want to get back the system to a original, you have to take extra heat. When the piston is expanding in the original process, there is a friction between the piston and the cylinder. As a result, there is some heat generated. Whatever the heat, extra heat generated, we have to take it out, right? Because we have to, in the reverse process, you have to get back the system to the same initial state. So whatever the heat that is generated, that we have to take it out. That means while giving, you are supplying 100, but that extra heat generated due to the friction, we have to take out extra. So such process will never happen practically, because there are so many practical things that will render, that will make a process irreversible. There are so many, I can give a big list. There are many practical parameters that will make a process irreversible. Reversibility is an imaginary, idealized, hypothetical process. When you eliminate all those irreversibilities, yes, in the limiting case you may achieve that reversible, but that is very practically difficult to achieve that thing. I am just listing out the factors. The factors that render a process irreversible. Why a process becomes irreversible? I am giving the fact why a process is irreversible. All practical processes or all real processes, to some extent or greater extent, they are all irreversible. Okay. After undergoing a thermodynamic process, if the system can be brought back to its initial state along the same path but in the reverse direction, we should not leave any evidence that that process has ever occurred. Supposing, imagine that like this. A person in the movies also you must have seen, a person jumping from the swimming pool on the ramp, from the ramp is jumped into the swimming pool. The same person landed in the water. Same person, imagine that is going back onto the ramp in the reverse direction from the water and going in the same path. That can be thought of as a reversible. Supposing a egg is there, just drop the egg, or accidentally fell off, broken. Can you get back all that inside things and you will get back the egg back? Or glass has broken, can you get back the glass again? So there are certain inherent natural things which becomes irreversible, Okay. The factors that render a process irreversible are main thing, mechanical rubbing friction. We can reduce it by using the lubrication, etc., but we cannot eliminate that. We can reduce the friction by using some lubrication or etc., point contact or ball bearings, etc., but we cannot eliminate that completely. Viscosity. See, whenever the fluid has got viscosity, there is some work. Fluid viscosity means what? Fluid friction. Whatever the work done against the viscous resistance will get converted into heat. That will one of the irreversibility. That will forever last. Heat transfer through a finite temperature difference. Heat transfer through a finite temperature difference. Supposing there is a 100 degrees Celsius body, there is a 50 degrees Celsius. Heat transfer happens, naturally happens, because heat transfer always occurs whenever there is a temperature difference. Now after that, both of them will arrive some thermal equilibrium condition. And can you get back that 150 again? Can you ask the heat to get back to the 150? It will never happen. Supposing Carnot proposed a different thing, different kind of a heat transfer. He proposed a heat transfer with no temperature difference, delta T 0 temperature difference. Such heat transfer can be thought of as a reversible. Heat transfer that occurs with no temperature difference, like in Carnot cycle. In the Carnot cycle, Carnot proposed a heat transfer with no temperature difference. One is 100, other is also 100. Delta T temperature difference is 0 with no temperature difference between giver and receiver. Is reversible. Electric resistance. Whenever some electric current passes through a resistance, a electric current is passing through a resistance. That resistance will get heated up. And now I have cooled the resistance. And again I have started supplying the heat to the resistance. I wanted the current back, current to go back. Can it happen? Never. So that is an irreversible. So that will render to the irreversibility. Electric resistance, non-adherence to equilibrium. Deviating greatly from thermodynamic equilibrium is one of the reasons for the irreversibility. Non-adherence to thermodynamic equilibrium. A quasi-static process, earlier I said, almost internally reversible. Why? The deviation of the system from thermodynamic equilibrium is infinitesimally small, very small. So because that can be quasi-static process can be treated as internally reversible process, because the deviation of the system from thermodynamic equilibrium is almost nil actually. Though it is deviating, even though the system is deviating from the thermodynamic equilibrium during the quasi-static process, the deviation being minutely small, so that can be thought of as internally reversible. So there are so many reasons: magnetic hysteresis, electric resistance, mechanical rubbing friction, heat transfer through a finite temperature difference. There are so many factors that will finally render a process irreversible. All the practical all the practical or real processes to some extent or greater, they are all irreversible. So, reversibility is a limit to your imagination. Reversible process is a limit to when all these things are absent, when all these, no viscosity, no electric resistance, in fact everything is thermodynamic equilibrium, adhering to thermodynamic equilibrium, and heat transfer is happening with no finite temperature difference. So, mixing of fluids, see, to mixing of two fluids is irreversible. A free expansion is irreversible. See, for example, fluid A, fluid B, and I remove the partition. A will diffuse into B, B will divide B. Mixing of fluids, mixing of two different fluids, after removing the partition. Is irreversible. Once the fluids get diffused into one another, can you get back the fluid on A on one side, B on the other side? Definitely, it is irreversible phenomenon. It's like that. So many things we could give. Okay. Thus, reversible process is a limit to our imagination or hypothetical or theoretical process. All practical processes are irreversible. All practical thermodynamic processes are irreversible to some extent or greater. Quasi-static process is internally reversible process. Okay, now having distinguished between reversible and irreversible, because I have listed only few, there are many more are there: magnetic hysteresis, viscosity, mixing of fluids. All this will contribute, all will render to the irreversibility of a thermodynamic process, heat transfer through a finite temperature difference. Okay, a glass is broken, it is an irreversible. Egg is falling and breaking, it is an irreversible process. Now, having finished this, having understood the reversible and irreversible process, now I would like to highlight laws of thermodynamics. Actually, laws of thermodynamics have no proof, but they are stated based on observing the nature. They are all natural laws. They don't carry any mathematical proofs. In the classical thermodynamics, whatever the laws that were stated, I already said thermodynamics history is around 250 to 300 years old. 18th century only it has started. All this, there are so many people who have contributed: Lord Kelvin, Clausius, Planck, including Einstein. Up to Einstein also have contributed something to the statistical thermodynamics. Boltzmann, so many people. Actually, thermodynamics has been developed over 2 to 3 centuries. Now it is enveloping all the branches of engineering: chemical, mechanical, civil, so many things, metallurgical, etc. it has 3 laws there. Actually, four laws are there, but fourth one is not that important at your BTech level. Zeroth law of thermodynamics. It defines a property called temperature. Which property is defined from zeroth law? Temperature. Then comes the first law of thermodynamics. This is only very important and easy also. First law of thermodynamics. It is defining a property called internal energy. From the first law only we get the internal energy. U, standard symbol is U. It is also known as a law of conservation of energy. First law of thermodynamics is also known as law of conservation of energy. Energy can neither be created nor destroyed. That is the first law of thermodynamics. But it has some limitations. It has some limitations there. And more prominent is the second law of thermodynamics. Second law of thermodynamics. From this law only we define a property called entropy, denoted by S. Temperature, internal energy and entropy. This is also known as law of degradation of energy. Second law of thermodynamics is also known as law of degradation of energy. If the first law is quantifying the energy, second law is qualifying the energy. Second law talks about the quality of energy. First law talks about the quantity of energy. Bookkeeping, energy bookkeeping, like how you keep the bookkeeping for the money. Supposing you have got 100 rupees in your pocket, 20 rupees you have spent, 30 rupees you have given to your friend, remaining 50 should be there. How you account for money? Like that you have to account for the energy according to the first law. First law, that is why it is called as a law of conservation of energy. In the eyes of first law, all energies are on the same footing, are on the same level, same pedestal. All energies are on the same pedestal, heat, work, everything, electrical energy, everything. But in case of this, in view of the second law, heat energy is an inferior energy, low grade energy, inferior energy. Whereas second law views the work as a high grade energy, high quality energy. Second law always says that high quality energy can be completely converted into the low quality energy, that is heat, low grade energy. But the reverse is not possible. We cannot completely convert this low grade energy of the heat completely into the work in a cyclic device. That is all about this second. That is why in view of the second law of thermodynamics, the heat is a lowest grade of energy. Its grade is low, inferior. All other forms like electrical, mechanical, potential energy of a body, all are superior energies. They can be easily degraded, very easily degraded into the low grade energy. But this is very difficult. From low grade energy to the high grade energy, this conversion is subjected to the second law. That is why it is something talk about the quality of energy. If the first law talks about the quantity of energy, second law talks about the quality of energy. Of course, there is one more law is also there, that is the third law of thermodynamics, but at your level that may not be that important. It talks about the absolute entropy. It talks about the absolute entropy at 0 Kelvin. It defines absolute entropy at 0 Kelvin. It defined, but that is not that important. We don't deal much about it, but we will be dealing all the remaining laws in detail. Now I will be defining the zeroth law of thermodynamics. This is the statement. When two thermodynamic systems namely A and B, and two thermodynamic systems namely A and B are independently in thermal equilibrium with a third system C are independently in thermal equilibrium with a third system C, then those two systems will be in with each other. When two thermodynamic systems are independently in thermal equilibrium with each other, with C. What do you mean by thermal equilibrium? First of all, we should understand that word thermal equilibrium. When two bodies are in, supposing a body is there, a hot body. I just kept that hot body in the atmosphere. Slowly the body keeps on getting cooled by convection, radiation, or whatever it is. A body, hot body kept in an atmosphere, slowly keep on getting cooled, and how long it will get cooled? Till it attains the same temperature as that of the surroundings. Once it attains the same temperature as that of the surroundings, any further heat transfer ceases, because the temperature of the body and the surroundings have become just equal. Then I say that the body is in thermal equilibrium with the surroundings. Thermal equilibrium means having the same temperature. Supposing my body is there, is it in thermal equilibrium with the surroundings? No. Why? My body temperature is 37 degrees Celsius. The surrounding air is at maybe now it is an AC room, maybe at 25 degrees Celsius. My body is not in thermal equilibrium with the surroundings. I am losing heat from my skin by convection. So this is not in thermal equilibrium. But definitely my body is in thermal equilibrium with another person sitting there, because his body temperature is also 37, my body temperature is also, we are in thermal equilibrium, because our both the bodies are at the same temperature, of course, assuming that neither me having fever nor he is having fever. None of that is having any fever. Yes, we are having the same temperature, we are in thermal equilibrium. So when two bodies are independently in thermal equilibrium with a third system C, then A and B must have the same temperature. All three thermodynamic systems must have the same temperature T. So from I can say that, so from zeroth law we can define the temperature as a thermodynamic property which decides whether a system is in thermodynamic equilibrium with the surroundings or not. So thus temperature T is a thermodynamic property of system which decides whether the system is in thermodynamic equilibrium with its surroundings or not. So, the temperature is a thermodynamic property. Of course, temperature in the physics also defined as a degree of hotness or a coldness. Then are there any scales to measure the temperature? Means yes, there is a scales of temperature, scales of measurement. We have the Celsius, we have the Fahrenheit, we have the Kelvin, we have the Ramer, so this is degrees Celsius, this is a degree Fahrenheit, this is a Kelvin. Generally, to convert one scale to another scale, I just give a point there, C by 100 F minus of course, Kelvin, to get the Kelvin, degrees Celsius plus 273.15 exactly, you can take approximately 273 then to get the Kelvin. So, this is the conversion. Like generally, there are usually we take the ice point and steam point, where the ice is melting into the water, that is ice point, where the steam is boiling into the water is boiling into the steam, that is a steam point. So, 0 degrees Celsius and 100 degrees Celsius on the Celsius scale, there are 100 divisions. In the Fahrenheit, that is there are 180 divisions there, 32 to 12. 32 plus 2, 32 is the Fahrenheit at a ice point and 212 is the steam point. For R it is 0 to 80, Ramer scale, it is an unconventional scale. For Kelvin, it is an absolute temperature scale or thermodynamic temperature scale, where the Kelvin is obtained by adding the 273 to the Celsius there. So, and one more thing is that thermodynamic temperature scale or the absolute temperature scale is independent of the nature of the working fluid what you are using in the thermometer. See, different thermometers use different thermometric fluids may be using, but the speciality of the absolute temperature scale or the thermodynamic temperature scale is that it is independent of the nature of the working fluid. That is one important speciality of the absolute, because that absolute temperature scale could also be derived from the Carnot theorems. That Kelvin temperature scale or the thermodynamic temperature scale or the absolute temperature scale can be derived from the Carnot theorems, which is wherein the working fluid does not have any role, because Carnot cycle efficiency is independent of the nature of the working fluid. So, that is why that they call it as the absolute temperature scale or a thermodynamic temperature scale. That particular scale is independent of the nature of the working fluid used in the thermometer. So, as such, the Kelvin temperature is obtained by adding 273.15 to the Celsius scale. So, from this particular formula we can convert once, if you are given a Celsius reading, you can convert into the Fahrenheit or you can convert into the Reamer, you can convert into the Kelvin. Okay. When you talk about the very fundamental law of thermodynamics called as the law of conservation of energy, I said. It could be having three different ways. For three different ways it can be written. For a cyclic process, for a non-cyclic process, undergone by closed system, for steady flow open system. This is also called as the SFEE, steady flow energy equation. This is also known as very famous equation. This is a law. I already said first law of thermodynamics is the law of conservation of energy. It accounts for energies. It keeps a bookkeeping for the energies. I am writing the mathematical formula also for a cyclic process. This is a non-cyclic process undergone by a closed system. This is the steady flow open system. With standard notations, Ke refer to the kinetic energy, Pe referring to the potential energy. Q minus W is delta H plus delta Ke plus delta Pe. Ke for kinetic energy and Pe for potential energy, H is the enthalpy. So this is the non-flow energy equation. Standard notation, U for the internal energy, H for the enthalpy. Here I am writing the small q and small w because I want to put the every term in a joule per kg. Every term in joule per kg, that is why I am putting a small letters there. Here of course it may be kilojoules. This circle refer to the a cyclic process. That could be a clockwise, it may be a clockwise cycle or anti-clockwise. Maybe clockwise or anti-clockwise. For both it will be valid. But one thing is certain, if a cycle is clockwise on the PV plane, it will also be clockwise on the TS plane. Generally, we usually at the BTech level, at your level, we use the two planes, PV and TS. As I mentioned, there are two more planes are there, HS and PH are also there, but that is not that important. But at your level, two PV, pressure volume, specific volume, temperature and specific entropy. And all speak about only one form, that energy can neither be created nor destroyed. You have to account for energies. We can't destroy the energy, we can't create the energy. And here the U is internal energy, the stored form of energy. It is the internal energy. It is the stored form of energy. Now first I will start with this for a first law for a cyclic process. Whenever a thermodynamic system undergoes a cyclic process, the net algebraic sum of heat transfers is directly proportional to the whenever a thermodynamic system undergoes a cyclic process, the net algebraic sum of heat transfers is directly proportional to the net algebraic sum of work transfers. This is the statement of the first law. So you have the sign convention, because when I say algebraic sum means sign convention. I already mentioned Q positive if supplied, negative if rejected from the system, W positive if work done by system, expansion, work is positive, negative if work done on the system. With this convention, we have to keep this convention in mind. Q is positive, Q is positive if supplied, negative if rejected. Supposing if you have a thermodynamic cycle, one to one. One to one is a thermodynamic cycle. For example, you have supplied Q here, say Q1 to 2 you have supplied, positive or negative according to the convention, positive. So during which their system might have done some work there. Work done by the system, it is also positive. Work done by the system, right? Because heat is supplied to the system here, it is positive. So maybe here heat has rejected, it should be treated as a negative rejection, no? And work may be supplied to the system, negative, because volume is decreasing, compression, work done on the system. Here rejection means negative. Say something like this is a rejection. It is a cycle, right? Cycle, what do you mean by thermodynamic cycle? Beginning at one thermodynamic state, after undergoing a number of processes, maybe 2, 3, 4, 5, cycle may have any number of processes. Beginning at one thermodynamic state, after undergoing 2, 3, here there are only 2, I have shown you through. But sometimes there may be 3, but most of the cycles have got 4 processes, most of the cycles, including Carnot. As I mentioned, only one cycle has 5, that is a dual cycle. One cycle has 3, that is a Lenard cycle. But for that, all other cycles will have 4 as such. So if we have this, for this particular first law of thermodynamics, if you see, cyclic integral of delta Q is equal to cyclic integral of delta W. So this is the first law. So according to this law, we have to add up all the heat transfers algebraically, taking the sign into account. Here, say for example, plus Q1 to 2. Why plus? Because heat supplied to the system. I have written here heat supplied to the system. Plus of minus Q2 to 1 must be equal to plus 1 to 2. Why plus 1 to 2? It is a work done by the system plus of minus work done on the system. Minus work done on the system, rejection, right? It is over here written. So according to the first law of thermodynamics, this any one unknown can be calculated here. Usually in the problems, 3 will be given. You have to calculate 1. But for that unknown, don't presume any sign. For example, Q221, W221 is asked. W221, you don't know whether it is a work done by the system or on the system, you don't know. Then take it as positive only. But based on the answer, you decide whether work is done on the system or by the system. Supposing W221, you got a negative answer. It means that work is done on the system. Suppose that W221 is a positive, that you got the answer in the. So that means if you W221 you obtain the positive answer, you should declare that work done by the system. Precaution here is, don't presume unknown sign, unknown quantity sign, whether heat or work. Supposing W221 is, you have to calculate. Take it as positive only. Supposing if the answer is obtained as a minus, then you say that heat is rejected. If the answer is obtained as positive, say that's applied. That means unknown quantity, don't presume the sign of negative or positive. Take it as positive only. Don't give it. But based on the answer you obtain, you decide. That is the precaution. So this is the law of conservation of energy, or first law written to a cyclic process. It is holds good for clockwise cycle and anti-clockwise cycle also. Anything. Here it is a clockwise cycle, which is a heat engine cycle. If it is an anti-clockwise cycle, means work absorbing cycle. Net work will be, supposing if the cyclic integral of delta W is negative, it is a refrigeration cycle or a work absorbing cycle. If this delta W, if this the cyclic integral of delta W, whole this quantity, if it is negative, say for example, then it is an anti-clockwise cycle or a refrigeration cycle. If the cyclic integral of delta W is positive, it is a heat engine cycle or a work producing cycle. So with this, today's class I am concluding, and tomorrow we will meet. Any doubts if you have, please post in our WhatsApp group. I have already we have mechanical engineering community group is there, or there is a doubt clarifying group is there. We can post it there. I will clear your doubts there.